Hundreds of millions of years ago, long before the world took the shape we know today, all land on Earth was joined together in one vast supercontinent. This enormous landmass, known as Pangea, stretched from pole to pole and held within it deserts larger than modern countries, endless forests and coastlines that faced a single massive ocean. Life flourished in ways both strange and spectacular. Reptiles grew to giant sizes, early dinosaurs emerged, and bizarre plants covered the land. It was a world of extremes, shaped by shifting climates and the slow, unstoppable movement of the Earth itself. Exploring Pangea reveals a story of survival and transformation, where landscapes twisted and cracked, and creatures adapted to a planet in constant motion. It was here that some of the most extraordinary chapters of Earth's history began, setting the stage for the rise of the dinosaurs. Before we dive into this ancient supercontinent, share in the comments where you're watching from and what time it is for you. Then get ready to journey back to the age of Pangea, a time when all the world was one. The story of Earth's continents before the emergence of Pangea is a tale of immense geological time, spanning billions of years and involving the slow, relentless dance of tectonic plates. Our planet began as a molten ball, a chaotic swirl of rock and metal, roughly 4.5 billion years ago. In its earliest phase, known as the Hadean Eon, the surface was too hot for solid land or liquid water to persist. Intense volcanic activity was constant, and the planet was frequently bombarded by asteroids and comets, remnants from the formation of the solar system. As the Earth gradually cooled, a thin, unstable crust began to form, only to be repeatedly melted and reformed by the planet's internal heat and external impacts. Over hundreds of millions of years, water vapor released from volcanic eruptions condensed to form the first oceans, and the continuous cooling allowed more stable, though still dynamic, land masses to emerge from the global ocean. These earliest continental fragments were small, likely no larger than modern-day islands or microcontinents, and were composed of primitive granitic rocks. During the Archean Eon, which followed the Hadean and lasted from approximately 4 billion to 2.5 billion years ago, the Earth's crust continued to thicken and stabilize. The process of plate tectonics, though perhaps operating differently than today, began to slowly assemble these small land masses into larger, more cohesive blocks. The exact configuration and timing of these early continental assemblies are difficult to reconstruct due to the immense age and subsequent geological reworking of the rocks. However, geological evidence suggests the formation of the very first protocontinents. These were not continents in the modern sense, but rather collections of smaller crustal pieces. One of the earliest proposed supercontinents, Volcanic, is thought to have formed around 3.6 billion to 3.1 billion years ago, comprising parts of what are now South Africa and Western Australia. Its existence is inferred from similarities in ancient rock formations and magnetic signatures. Following Volcanic, another early supercontinent, Ur, is hypothesized to have formed about 3 billion years ago. Ur was not a global supercontinent, but was likely the largest landmass on Earth at the time, containing parts of modern-day Africa, India, and Australia. These early continental nuclei were relatively stable and grew over time through the accretion of volcanic island arcs and smaller crustal fragments. The Proterozoic Eon, from 2.5 billion to 541 million years ago, witnessed significant advancements in both continental assembly and the evolution of life. This eon is characterized by the formation and breakup of several major supercontinents, a cycle that would eventually lead to Pangea. Around 2.7 billion to 2.5 billion years ago, the supercontinent Kenneland is believed to have formed, encompassing large parts of what are now North America, Greenland, Scandinavia, and parts of Siberia. Kenneland's breakup, driven by mantle plumes and rifting, occurred around 2.4 billion to 2.1 billion years ago, leading to widespread glaciation events, possibly due to changes in atmospheric carbon dioxide levels. Following Kenneland, the supercontinent Columbia, also known as Nuna, assembled between 2.1 billion and 1.8 billion years ago. Columbia was a vast landmass that included nearly all of Earth's continental blocks at the time, stretching from what is now North America to Siberia, Australia, and Antarctica. Its formation involved a series of continent-continent collisions, creating extensive mountain belts. Columbia remained stable for several 100 million years before beginning to fragment around 1.3 billion years ago. The most well-understood supercontinent preceding Pangea was Rodinia, which assembled around 1.1 billion years ago. Rodinia was a massive landmass centered near the equator, and its formation involved the collision of several continental blocks, including Laurentia, Proto-North America, Baltica, Proto-Europe, Siberia, Amazonia, and the vast landmass of Gondwana. The assembly of Rodinia resulted in the closure of ancient oceans and the formation of extensive mountain ranges. The climate during Rodinia's existence was complex, with evidence suggesting periods of extreme cold, including the snowball Earth events, where the planet may have been almost entirely covered in ice. The breakup of Rodinia began around 750 million years ago, a process that was slow and protracted, continuing for hundreds of millions of years. This breakup created new ocean basins, such as the Iapetus Ocean and the Panthallassic Ocean, and led to the dispersal of continental fragments. These fragments would eventually reassemble in new configurations. Alongside these grand geological transformations, life on Earth was also undergoing profound changes. The very first life forms were single-celled organisms, prokaryotes, that emerged in the Archean Eon, perhaps as early as 3.8 billion years ago, thriving in the primordial oceans. These early life forms were anaerobic, meaning they did not require oxygen, as the early Earth's atmosphere had very little free oxygen. Around 3.5 billion years ago, photosynthetic organisms, particularly cyanobacteria, began to evolve. These microscopic life forms use sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. This seemingly simple biological innovation had a revolutionary impact on the planet. Over hundreds of millions of years, the cumulative effect of oxygen production by cyanobacteria led to the Great Oxidation Event around 2.4 billion to 2.1 billion years ago. This event saw a dramatic increase in atmospheric oxygen levels, which was toxic to many existing anaerobic life forms, but paved the way for the evolution of more complex oxygen-breathing organisms. Evidence of these early photosynthetic communities can be found in ancient stromatolites, layered rock structures formed by microbial mats. The Proterozoic eon also saw the emergence of eukaryotes, cells with a nucleus and other complex internal structures, around 2 billion to 1.5 billion years ago. This was a crucial step towards multicellular life. The exact origins of eukaryotes are still debated, but they represent a significant leap in biological complexity. Later in the Proterozoic, particularly during the Neoproterozoic era, 1 billion to 541 million years ago, the first multicellular organisms began to appear. The Ediacaran biota, dating back to around 600 million to 541 million years ago, represents some of the earliest known complex multicellular life forms. These were soft-bodied organisms, often flat and disc-shaped, that lived on the seafloor. They lacked hard parts like shells or bones, which makes their fossil record sparse and difficult to interpret. But they provide a glimpse into a world before the explosion of diverse animal forms. The breakup of Rodinia and the subsequent changes in ocean chemistry and climate, including the snowball Earth events, are thought to have played a role in spurring the evolution of these early complex life forms. The final stages before Pangea's formation involved the continued drift of these continental fragments, setting the stage for their eventual collision and the grand assembly of the supercontinent that would host the age of dinosaurs. The formation of Pangea was a monumental geological event, the culmination of hundreds of millions of years of continental drift and collision, driven by the powerful forces of plate tectonics within the Earth's mantle. This supercontinent, meaning all lands in ancient Greek, began its assembly in the late Paleozoic era, primarily during the Carboniferous and Permian periods, roughly 350 million to 250 million years ago. It was not a single, sudden event, but a protracted process involving the convergence and amalgamation of several large continental blocks that had previously separated from earlier supercontinents like Rodinia and Columbia. The primary players in this grand collision were two immense landmasses, Gondwana, a southern supercontinent comprising what would become South America, Africa, Antarctica, Australia and India, and Laurasia, a northern supercontinent made up of what would become North America, Europe, and Asia, excluding India. The initial stages of Pangea's formation involved the closure of several ancient oceans. One of the most significant was the Rhaetic Ocean, a vast body of water that separated Gondwana from the continental fragments that would eventually form Laurasia. As the tectonic plates carrying these land masses moved towards each other, the oceanic crust of the Rhaetic Ocean was subducted or pulled down beneath the overriding continental plates. This process led to intense volcanic activity and the formation of island arcs, similar to modern-day Japan or the Andes. The collision itself was not a single impact, but a series of progressive dockings of various continental fragments. For instance, the microcontinent of Avalonia, which included parts of modern-day Britain and eastern North America, collided with Laurentia, proto-North America, during the Devonian period, around 390 million years ago. This collision, known as the Acadian orogeny, contributed to the growth of the Appalachian mountain chain in eastern North America. As the Carboniferous period progressed, the major collision between Gondwana and Laurasia intensified. Gondwana, moving northward, began to collide with the southern margin of Laurasia. This immense collision, often referred to as the Variscan or Hercynian orogeny in Europe and the Alleghenian orogeny in North America, was one of the most significant mountain-building events in Earth's history. It resulted in the uplift of vast mountain ranges that stretched across the newly forming supercontinent. The Appalachian Mountains, which extend from eastern North America to parts of Greenland and Scandinavia, are a direct remnant of this collision. Similarly, the Ural Mountains, which form a natural boundary between Europe and Asia, were formed by the collision of the Siberian Craton with Baltica, Proto-Europe, during the late Carboniferous and early Permian periods, around 300 million to 280 million years ago. These mountain ranges were far more massive and extensive than their modern counterparts, having been subjected to hundreds of millions of years of erosion. The final stages of Pangea's assembly involved the rotation and fitting together of these large continental blocks. By the early Permian period, around 280 million years ago, most of the major landmasses had amalgamated. The supercontinent was roughly C-shaped, with the Tethys Ocean forming a large embayment on its eastern side. The vast global ocean surrounding Pangea was named Panthalassa, or All Seas. The interior of Pangea was immense, stretching from pole to pole, and its sheer size had profound effects on global climate and ocean circulation. The formation of Pangea also led to the closure of other smaller ocean basins, such as the Paleo-Tethys Ocean. As continental blocks moved closer, the process was akin to a slow-motion, colossal jigsaw puzzle, with pieces grinding and locking into place over millions of years, driven by the convection currents within the Earth's mantle. The mechanism behind this continental movement is plate tectonics, a theory that explains how the Earth's rigid outer layer, the lithosphere, is broken into large plates that are constantly moving. These plates float on the semi-fluid asthenosphere beneath them. Heat from the Earth's core creates convection currents in the mantle, causing the asthenosphere to slowly flow. This flow drags the overlying tectonic plates, leading to their movement across the Earth's surface. When plates converge, they can collide, causing mountain building, or one plate can subduct beneath another. When plates diverge, new oceanic crust is formed at mid-ocean ridges. The formation of Pangea was a prime example of convergent plate boundaries, where continental plates, being too buoyant to subduct, crumpled and uplifted to form massive mountain ranges. The energy released during these collisions was immense, causing widespread seismic activity and metamorphism of existing rocks. The geological evidence for Pangea's existence and its formation is extensive and comes from various sources. One of the earliest pieces of evidence was the remarkable fit of the continents, particularly the eastern coast of South America with the western coast of Africa, first noted by early cartographers. Further support came from the distribution of ancient fossils. Identical fossil species of plants and animals, such as the freshwater reptile Mesosaurus and the fern Glossopteris, are found on continents now separated by vast oceans, indicating that these landmasses must have once been connected. The presence of similar rock types and geological structures across different continents also provides strong evidence. For example, the same sequence of rock layers and ancient mountain belts can be traced from the Appalachian Mountains in North America to the Caledonian Mountains in Scandinavia and the Atlas Mountains in North Africa, all remnants of the same colossal collision that formed Pangea. Paleomagnetism, the study of the Earth's ancient magnetic field preserved in rocks, provides further compelling evidence. As molten rock cools and solidifies, magnetic minerals within it align with the Earth's magnetic field at that time. By studying the orientation of these magnetic minerals in rocks of different ages from various continents, scientists can reconstruct the past positions of the continents relative to the magnetic poles. These paleomagnetic data consistently show that the continents were once joined in the configuration of Pangea. Furthermore, evidence of ancient glaciations, such as glacial striations and tillites, rock deposits formed by glaciers, found in tropical regions of modern continents like India, Africa and South America, can only be explained if these land masses were once located together near the South Pole as part of Gondwana within Pangea. The formation of Pangea was a truly global event, reshaping the Earth's surface and setting the stage for the unique climatic conditions and the evolution of life that would characterize the Mesozoic era. Its assembly was a testament to the continuous powerful forces that shape our planet over geological timescales. The climate of Pangea was profoundly different from the Earth's climate today, largely due to the supercontinent's immense size and its unique configuration. With nearly all of the Earth's landmass consolidated into one vast continent, the moderating influence of oceans on temperature and weather patterns was significantly reduced, especially in the interior. This led to extreme seasonality and widespread aridity across much of the supercontinent. The Permian period, during which Pangea fully assembled, began with a significant ice age, a remnant of earlier glaciations. Large ice sheets covered parts of Gondwana, particularly what is now Antarctica, Australia, India, and southern Africa. As Pangea continued to form and drift northward, these ice sheets gradually retreated, and the climate generally warmed throughout the Permian and into the Triassic and Jurassic periods. One of the most defining characteristics of Pangea's climate was the extreme temperature variations between seasons. Coastal regions, particularly those bordering the vast Panthalassa Ocean, would have experienced more moderate temperatures due to the ocean's thermal buffering effect. However, the immense interior of Pangea was far removed from any oceanic influence. This meant that continental interiors experienced scorching hot summers, with temperatures potentially reaching very high levels, and bitterly cold winters, possibly dropping below freezing even in what are now temperate zones. The absence of significant mountain ranges running east-west across the central part of the supercontinent also meant that air masses could move freely across vast distances, leading to less localized weather and more widespread extreme conditions. The sheer scale of the landmass amplified continental climate effects, creating a climate regime unlike anything seen on Earth in recent geological history. The global atmospheric circulation patterns were also significantly altered by Pangea's configuration. Without multiple continents to break up and channel air currents, the Hadley, Ferrel and polar cells, which drive global wind patterns, would have operated on a much larger scale. This likely resulted in very strong monsoonal systems, particularly around the Tethys Sea, a large embayment on Pangea's eastern side. During certain seasons, warm, moist air from the Tethys Ocean would have been drawn inland, bringing heavy rainfall to coastal and near-coastal regions. In other seasons, dry air would have flowed outwards from the interior, leading to prolonged droughts. However, the deep interior of Pangea would have remained largely unaffected by these monsoonal rains, leading to widespread desertification. Evidence for these vast deserts comes from extensive deposits of red beds, sandstones and evaporites, minerals formed from the evaporation of water, found in the geological record of the Permian and Triassic periods across many modern continents that were once part of Pangea. The lack of numerous shallow epicontinental seas, which are common today and help regulate global temperatures, also contributed to Pangea's extreme climate. Modern continents are often bordered by shallow seas that absorb and release heat slowly, moderating coastal temperatures. Pangea, with its vast, uninterrupted landmass, had fewer such moderating influences. The Panthalassa Ocean, while enormous, was a deep ocean, and its thermal influence was primarily limited to the immediate coastlines. The Tethys Sea was an exception, providing a more temperate and humid environment along its shores. This meant that the majority of Pangea's land area was subject to a highly continental climate, characterized by low humidity, clear skies, and large diurnal, day-night temperature swings, in addition to the extreme seasonal variations. The distribution of flora and fauna across Pangea was directly influenced by these climatic conditions. The vast deserts of the interior would have supported only specialized drought-resistant plant life, while the more humid coastal and equatorial regions, particularly those influenced by the Tethys Sea, would have hosted lush forests. For example, the Permian period saw the dominance of gymnosperms, such as conifers and cycads, which are well adapted to drier conditions, replacing the widespread coal swamps of the Carboniferous period. These plants were more resilient to temperature extremes and water scarcity. The animals that inhabited Pangea also had to adapt to these challenging conditions. Many reptiles, with their scaly skin and efficient water retention, were particularly well suited to the arid environments. Early dinosaurs, which emerged in the Triassic period, evolved in a world shaped by these extreme climatic pressures, developing adaptations that allowed them to thrive in varied environments across the supercontinent. As Pangea began to break apart in the Jurassic period, the climate started to change. The opening of new ocean basins, such as the Central Atlantic Ocean, allowed more water to penetrate the continental interiors, gradually increasing humidity and moderating temperatures. The fragmentation of the supercontinent also altered global ocean currents. When Pangea was intact, the Panthalassa Ocean had a single, vast, circum-equatorial current that flowed around the supercontinent. This current would have transported warm water across the globe, but its immense size and lack of obstructions might have limited the mixing of ocean waters and the distribution of heat. As the continents drifted apart, new ocean gateways opened, allowing for more complex and varied ocean circulation patterns, which in turn influenced global climate by redistributing heat more effectively. The geological record provides substantial evidence for Pangea's climate. Extensive coal deposits from the Carboniferous period, found across continents that were once part of Pangea, indicate widespread tropical swamps and forests in the regions that were then near the equator. The shift to red beds and evaporates in the Permian and Triassic periods, found in areas that would have been in the dry interior of Pangea, strongly supports the existence of vast deserts. Fossil evidence also aligns with these climatic interpretations. For instance, the types of plants and animals found in different regions of Pangea correspond to the predicted climate zones. The study of ancient soils, known as paleosols, also provides clues about past rainfall and vegetation. The Pangean climate was a powerful selective force, shaping the evolution and distribution of life on Earth for tens of millions of years, leading to unique ecosystems adapted to its extreme conditions. The physical geography of Pangea was a landscape of monumental scale, profoundly shaped by the very forces that assembled it. This supercontinent, a singular landmass encompassing nearly all of Earth's continental crust during the late Paleozoic and early Mesozoic eras, presented a panorama of vast mountain ranges, expansive deserts, and extensive coastlines bordering a singular global ocean. Its sheer size, stretching from one pole to the other, meant that Pangea contained an unparalleled diversity of terrestrial environments, though many of these were extreme by modern standards. The orogenic events, or mountain-building collisions that led to Pangea's formation, left an indelible mark on its topography, creating mountain chains that dwarfed contemporary ranges. One of the most prominent geographical features of Pangea was its extensive system of mountain belts. These ranges were formed by the immense pressure and crumpling of crust as continents collided. The Appalachian Mountains, a dominant feature of eastern North America today, are but a heavily eroded remnant of a much larger chain known as the Central Pangean Mountains. This colossal mountain system extended from what is now the southeastern United States, through eastern North America, across parts of Greenland, through what is now the British Isles, and into parts of Central Europe, where it is known as the Hercynian or Voriscan mountain belt. This range was comparable in scale and height to the modern Himalayas at its peak, rising many thousands of meters above sea level. It was created primarily by the collision of Gondwana with Laurentia, Proto-North America, and Baltica, Proto-Europe, during the Alleghenian and Variscan orogenies, which occurred from approximately 320 million to 280 million years ago. These mountains acted as a significant barrier to atmospheric circulation, influencing precipitation patterns and creating rain shadows that contributed to the aridity of the supercontinent's interior. The erosion of these ancient mountains provided vast quantities of sediment, which were deposited in basins across Pangea, forming the red rock layers characteristic of the Permian and Triassic periods. Further east on Pangea, another major mountain range, the Urals, was formed by the collision of the Siberian Craton with Baltica. This collision, which concluded by the early Permian around 280 million years ago, created a long north-south trending mountain chain that marked a significant internal boundary within the eastern part of Pangea. These mountains, though not as high as the central Pangean chain, still represented a formidable topographical barrier. The continued tectonic activity also led to smaller, localized mountain building events and uplifted plateaus throughout the supercontinent. These elevated regions, coupled with the vastness of the landmass, profoundly influenced river systems. Major rivers would have flowed from these highlands, traversing enormous distances across the continental interior before reaching the coast. These ancient river valleys would have been vital arteries for the dispersal of life and the transport of sediments, creating fertile floodplains in an otherwise arid interior. The vast interior of Pangea was characterized by extensive deserts and arid plains. This extreme aridity was a direct consequence of the supercontinent's size and shape. Being so far from the moderating influence of any large ocean, the central regions experienced very low precipitation. Moisture-laden air masses from the Panthalassa Ocean would have lost most of their water vapor as they travelled over the distant mountain ranges and vast land area before reaching the interior. This continentality effect created an immense rain shadow, resulting in hyper-arid conditions. Geological evidence for these deserts comes from thick sequences of Aeolian sandstones, indicative of ancient dune fields and extensive evaporate deposits, formed when large bodies of water evaporated in arid conditions, leaving behind salt and gypsum. These desert environments would have been stark and challenging for life, favouring specialised, drought-resistant plant life. Coastal regions of Pangea were diverse, reflecting the supercontinent's irregular shape and its interaction with the Panthalassa Ocean and the Tethys Sea. The western and northern coasts bordering Panthalassa would have been expansive, long stretches of shoreline, possibly with wide coastal plains and deltic systems where major rivers emptied into the global ocean. These areas would have experienced more moderate temperatures and higher humidity compared to the interior, supporting more lush vegetation. The eastern side of Pangea was dominated by the large wedge-shaped Tethys Sea, which indented deeply into the supercontinent. The coasts along the Tethys were likely characterized by warmer, shallower waters, extensive carbonate platforms and vibrant marine ecosystems. This embayment created a more humid, subtropical climate along its shores, contrasting sharply with the arid interior just a few hundred kilometers away. The shape of the coastline influenced ocean currents, creating upwelling zones in some areas that brought nutrient-rich waters to the surface, supporting abundant marine life. The overall configuration of Pangea was that of a massive, roughly C-shaped landmass, with the Tethys Sea on its concave eastern side. This shape was important for its geological and climatic evolution. The northern part of Pangea, Laurasia, included what would become North America and Eurasia. The southern part, Gondwana, contained present-day South America, Africa, Antarctica, Australia and India. The suture zones, where these vast continents collided, were areas of intense deformation and mountain building. Beyond the major mountain ranges and deserts, Pangea would also have featured vast shield areas, ancient stable blocks of continental crust that had remained relatively undisturbed for billions of years. These shield areas, such as the Canadian Shield or the African Craton, would have formed the low-lying, stable cores around which the supercontinent assembled. The long-term erosion of Pangea's high mountain ranges slowly transformed its topography over tens of millions of years. Rivers carried vast quantities of eroded material, filling sedimentary basins and contributing to the formation of extensive sedimentary plains. The relatively flat, low-lying regions within the supercontinent, particularly those not affected by mountain building, would have been vast plains, perhaps supporting unique ecosystems. The presence of large lakes and inland seas within these plains would have been intermittent, highly dependent on erratic rainfall patterns in the interior. The geological record of Pangea's geography is preserved in the rock formations found on modern continents. For example, the distinctive red sandstones and shales found across the southwestern United States, Europe, and parts of Africa speak to the widespread arid conditions and vast desert environments that once covered the heart of the supercontinent. The scars of ancient mountain ranges, now worn down to their roots, also testify to the immense forces that shaped this unique ancient world. The Panthalassa Ocean was the single immense global ocean that surrounded the supercontinent Pangea during the late Paleozoic and early Mesozoic eras, from approximately 320 million to 175 million years ago. Its name, derived from ancient Greek, means all seas, aptly describing its vastness. This ocean covered approximately 70% of the Earth's surface, making it significantly larger than the Pacific Ocean, which is the largest ocean basin today. The sheer scale of Panthalassa meant that it had unique characteristics regarding its depth, currents, and marine life, differing substantially from the fragmented ocean basins of the modern Earth. The size of Panthalassa meant that its deep water regions were exceptionally vast and deep. While specific depths varied across the basin due to underwater mountain ranges, trenches, and abyssal plains, the average depth would have been considerable, likely exceeding that of modern oceans in many areas. Mid-ocean ridges, where new oceanic crust was continuously being formed as tectonic plates diverged, would have traversed the Panthalassa floor, similar to the mid-Atlantic ridge today, but on a grander scale. These underwater mountain chains would have been sites of volcanic activity and hydrothermal vents, supporting unique chemosynthetic ecosystems, similar to those found in modern deep-sea vents, thriving on chemical energy rather than sunlight. Trenches, formed where oceanic crust was subducted beneath continental or other oceanic plates, would have marked the edges of the Panthalassa basin, particularly along the active margins where Pangea was colliding with oceanic plates. These trenches would have represented the deepest parts of the ocean. One of the most defining features of Panthalassa was its unique current system, with Pangea forming a single, massive land barrier across much of the Earth's longitude. Panthalassa would have hosted a dominant circumequatorial current. This powerful current, driven by prevailing winds, would have flowed continuously around the supercontinent, distributing warm water across vast distances. This might have led to relatively uniform surface temperatures across broad areas of the tropical Panthalassa. However, the immense size of the ocean, coupled with the single strong circumequatorial current, likely limited the global mixing of ocean waters. This could have resulted in reduced upwelling of nutrient-rich deep waters in some areas, potentially affecting marine productivity in open ocean regions. The lack of distinct smaller ocean basins and the absence of a strong north-south continental barrier also meant that major currents, like the Gulf Stream or Kuroshio Current of today, which transport heat to higher latitudes, would not have existed in the same way. This might have contributed to the extreme climate differences between the coasts and the interior of Pangea. The marine life of Panthalassa, particularly during the Mesozoic era, was diverse, though perhaps less varied than in the more fragmented oceans that followed. In the Permian period, before the full bloom of the age of dinosaurs, fish, sharks, and various types of invertebrates were prevalent. As the Triassic period began, the ocean saw the proliferation of ammonites, a group of shelled cephalopods that resembled modern nautiluses. These creatures were highly successful and left an extensive fossil record, serving as important index fossils for dating marine sediments. Other invertebrates included bivalves, gastropods, and various crustaceans. By the mid-Triassic, the first large marine reptiles began to evolve, adapting to life in the vast ocean. Ichthyosaurs, with their dolphin-like bodies and powerful tails, were efficient predators, while plecodonts were specialized in crushing shellfish with their flat teeth. Plesiosaurs, with their long necks and 4 large flippers, also emerged, becoming significant predators. As the Jurassic and Cretaceous periods unfolded, Panthalassa continued to be the domain of these marine giants. Ichthyosaurs reached their peak diversity, and plesiosaurs evolved into larger, more varied forms, including the short-necked pliosaurs, which were apex predators. Mosasaurs, giant marine lizards, became dominant predators in the late Cretaceous, following the decline of some earlier marine reptile groups. Sharks continued to be important predators, evolving into many of the forms recognizable today. The presence of a single, vast ocean also meant that marine species could potentially disperse over very long distances, leading to less regional variation in marine faunas compared to a world with multiple separated oceans. However, the immense distances and the uniformity of the deep ocean environment might have also limited the evolutionary pressures that drive diversification in smaller, more geographically isolated basins. The deep parts of Panthalassa remain largely a mystery due to the ongoing process of seafloor spreading and subduction. Oceanic crust is constantly being created at mid-ocean ridges and consumed at subduction zones. This means that very little of the ocean floor from the time of Panthalassa has been preserved. Most of it has been recycled back into the Earth's mantle over hundreds of millions of years. Therefore, direct geological evidence from the ancient Panthalassa seabed is rare, making reconstructions of its deep sea environment challenging. Scientists rely on indirect evidence, such as the fossil record of marine organisms found in continental shelf deposits that were once part of Panthalassa's margins, and the principles of plate tectonics and oceanography to infer its characteristics. Despite the challenges, the concept of Panthalassa is crucial for understanding the paleogeography and paleoclimate of the dinosaur era, as its vast expanse and unique circulation patterns profoundly influenced the conditions on the supercontinent Pangea. The Tethys Sea was a significant and dynamic ocean, or more accurately, a complex system of oceanic embayments and gulfs that existed during the Mesozoic era, when Pangea was the dominant landmass. It was a large, wedge-shaped body of water that deeply indented the eastern and southeastern side of the supercontinent. Unlike the vast and open Panthalassa ocean that surrounded Pangea, the Tethys was an interior sea, forming a vital connection between the eastern Panthalassa and smaller, more restricted basins to the west. Its position, mostly within tropical and subtropical latitudes, made it a warm, relatively shallow, and biologically rich marine environment. Its evolution was intimately linked with the breakup of Pangea and the formation of modern continents. The Tethys Sea's origins can be traced back to the Paleo-Tethys Ocean, which existed before the full assembly of Pangea. As Pangea formed, the Paleo-Tethys began to close, and a new embayment, the Neo-Tethys, began to open, eventually becoming the Tethys Sea proper. By the Jurassic period, around 200 million years ago, the Tethys was a prominent feature of Earth's geography. It stretched eastward from where the Mediterranean Sea is today, extending across what is now southern Europe, North Africa, and much of Asia, reaching into Southeast Asia. Its width and depth varied significantly along its extent, with some areas being shallow shelves and others forming deep oceanic basins. The Tethys Sea served as a crucial marine gateway, allowing for the exchange of marine life and ocean currents between the eastern and western parts of the global ocean system. The Tethys Sea was characterized by its warm, tropical to subtropical waters. Its position near the equator and its relative shallowness in many areas contributed to higher sea surface temperatures compared to the deeper open Panthalassa Ocean. This warmth, combined with sunlight penetration to the seafloor in shallow regions, created ideal conditions for the flourishing of diverse marine life. Extensive carbonate platforms, similar to modern-day coral reefs, developed along its margins. These platforms were built by various marine organisms, including calcareous algae, sponges, and eventually scleractinian corals, which proliferated in the warm, clear, nutrient-rich waters. The Tethys acted as a major centre of marine biodiversity, fostering the evolution and diversification of numerous species. The marine life within the Tethys Sea was exceptionally rich and varied. It hosted a wide array of invertebrates, including abundant ammonites, belemnites, squid-like cephalopods, bivalves, like clams and oysters, gastropods, snails, and echinoderms, like sea urchins and starfish. The warm waters were also teeming with various types of fish, from small bony fish to larger sharks and rays. The Tethys was a vital habitat for many of the iconic marine reptiles of the Mesozoic era. Ichthyosaurs, with their streamlined, fish-like bodies, were common predators. Plesiosaurs, with their long necks and flippers, and the short-necked, powerful plesiosaurs also hunted in its waters. In the late Cretaceous, mosasaurs, giant marine lizards, became dominant, preying on fish and other marine reptiles. The relatively enclosed nature of the Tethys, compared to the open Panthalassa, may have led to distinct evolutionary pathways and specialized ecosystems within its confines, increasing overall marine biodiversity. The Tethys Sea played a critical role in influencing the climate of the adjacent Pangean landmasses. Its warm waters and presence within the landmass provided a source of moisture, leading to more humid and monsoonal conditions along its shores compared to the arid interior of Pangea. This resulted in more lush vegetation and less extreme temperatures in regions bordering the Tethys. For example, parts of what are now Europe, the Middle East and Southeast Asia, which were once Tethyan coastal regions, would have supported diverse plant and animal communities that thrived in more humid tropical environments. The interaction between the Tethys and the global atmospheric circulation patterns contributed to distinct climate zones within Pangea, creating a gradient from the hyper-arid interior to the more temperate and humid coastal fringes. The geological history of the Tethys Sea is complex and spans hundreds of millions of years. It was not a static body of water, but underwent continuous changes in its shape, size and depth due to the ongoing movements of tectonic plates. As Pangea began to break apart, the Tethys Sea expanded, becoming a major ocean basin. The opening of the Atlantic Ocean and the eastward movement of the African and Indian plates squeezed and eventually closed large parts of the Tethys. The remnants of the Tethys Sea are still visible today in the geological structures of the Mediterranean Sea, the Black Sea, the Caspian Sea, and the mountain ranges that stretch from the Alps through the Himalayas. These mountain ranges, known as the Alpine-Himalayan orogenic belt, were formed by the immense collisions of continental blocks that once bordered the Tethys, such as the collision of the Indian plate with Asia and the African plate with Europe. These ongoing collisions have uplifted vast quantities of marine sediments and ancient oceanic crust from the Tethys Sea, providing invaluable fossil evidence of its once thriving ecosystems and the warm, shallow conditions that prevailed there. The Tethys Sea thus represents a crucial chapter in Earth's paleogeography, serving as both a bridge between ancient oceans and a cradle for diverse marine life during the age of dinosaurs. The plant life that covered Pangea during its existence, spanning from the late Permian through the Triassic and Jurassic periods, formed the foundational base of the entire terrestrial food web. Unlike the modern world dominated by flowering plants, the Pangean flora was characterized by a different set of dominant groups, primarily gymnosperms, ferns, and their relatives. These plants had to contend with the unique climatic conditions of the supercontinent, particularly its vast arid interiors and pronounced seasonality. Their adaptations to these challenges shaped the ecosystems that supported the emerging dinosaurs and other land animals. In the early Permian period, as Pangea was fully assembling, the plant communities still bore some resemblance to those of the preceding Carboniferous period, especially in more humid regions. Extensive coal swamps, rich in giant club mosses, horsetails and tree ferns, were present in equatorial and coastal areas. These plants thrived in wet, marshy environments. However, as the Permian progressed and the supercontinent consolidated, the climate became increasingly arid across much of the interior. This environmental shift favoured the rise of seed plants, particularly gymnosperms, which were better adapted to drier conditions than spore-bearing plants. Gymnosperms, meaning naked seeds, produce seeds that are not enclosed within an ovary, unlike flowering plants. This evolutionary innovation allowed them to reproduce without needing standing water for fertilization, a significant advantage in a drying world. Among the most widespread and ecologically important gymnosperms of Pangea were the conifers. These included ancestors of modern pines, spruces and firs, as well as extinct groups. Conifers were well suited to the varied Pangean environments, from temperate zones to more arid regions. Their needle-like or scale-like leaves had a reduced surface area, minimizing water loss, and their thick, waxy cuticles provided further protection against desiccation. Conifer forests would have covered vast swathes of Pangea, providing shelter and food for many terrestrial animals. Another prominent group of gymnosperms were the cycads. These plants resembled modern palms or ferns, with stout, unbranched trunks and a crown of large, stiff, fern-like leaves. Cycads were particularly abundant in tropical and subtropical regions of Pangea, forming a significant component of the undergrowth and providing a food source for herbivorous dinosaurs. They are often referred to as living fossils because their form has changed little over millions of years. Ginkgos, represented today by the single species Ginkgo biloba, were also common across Pangea. Ancient ginkgo trees had distinctive fan-shaped leaves and were deciduous, shedding their leaves seasonally, an adaptation to cope with periods of drought or cold. Their presence indicates areas with distinct seasonal changes. Another important group, especially in the southern parts of Pangea, Gondwana, was the Glossopteris flora. Glossopterids were a type of seed fern, a group of extinct plants that reproduced by seeds but had fern-like leaves. The distribution of Glossopteris fossils across South America, Africa, India, Antarctica, and Australia was one of the key pieces of evidence supporting the theory of continental drift and the existence of Pangea. These plants were well adapted to cooler, possibly even glaciated conditions in the high-latitude regions of Gondwana during the early Permian, before the full extent of Pangea's aridity took hold. While gymnosperms dominated, ferns and horsetails still thrived in localized, more humid environments, such as along riverbanks, lake shores, and in coastal lowlands. These spore-bearing plants required moist conditions for reproduction, as their sperm needed water to swim to the egg. Giant horsetails, similar to modern equisetum but much larger, formed dense stands in marshy areas. Various types of ferns, from ground-hugging species to tree ferns, would have provided ground cover and mid-level vegetation in suitable habitats. These plants were a crucial food source for smaller herbivores and insects. The absence of flowering plants, or angiosperms, during most of Pangea's existence meant that the plant landscape looked very different from today. Angiosperms only began to diversify significantly in the mid-Cretaceous period, long after Pangea had begun to break apart. Their absence meant that the co-evolutionary relationships between plants and pollinating insects or fruit-eating animals were also different. The plant communities of Pangea formed the base of the ancient food web, converting sunlight into energy through photosynthesis and providing sustenance for all other terrestrial life. Herbivorous animals, from large reptiles to early mammal-like creatures and eventually dinosaurs, directly consumed these plants. The types of plants available influenced the evolution of herbivore dentition and digestive systems. For example, the tough, fibrous nature of gymnosperm leaves would have required strong jaws and specialized teeth for grinding. The vastness of Pangea meant that different plant communities developed in response to regional climatic variations. The interior deserts supported sparse, hardy vegetation, while the coastal areas and regions influenced by the Tethys Sea could sustain more diverse and lush forests. The spread of plant species across Pangea was facilitated by the continuous landmass, allowing for wider dispersal than would be possible on fragmented continents. However, climatic barriers, such as vast deserts or high mountain ranges, could still limit the distribution of certain plant groups. For instance, the Glossopteris flora was largely confined to Gondwana, reflecting its adaptation to southern high-latitude conditions. The evolution of seed plants was a critical adaptation to the changing global climate, enabling plants to colonize drier environments and expand their range across the supercontinent. The seeds provided a protective coat for the embryo and a food supply, allowing for greater dispersal and survival in challenging conditions. The success of these ancient plants laid the ecological groundwork for the subsequent diversification of a large terrestrial herbivores, including the plant-eating dinosaurs that would come to dominate the Mesozoic landscape. Before the reign of the dinosaurs, the land masses that would eventually coalesce into Pangea were home to a diverse array of terrestrial animals. These creatures, primarily evolving during the Permian period, represented a crucial transitional phase in vertebrate evolution, bridging the gap between amphibians and the more advanced reptiles and mammal-like animals. Their adaptations to the increasingly continental and arid conditions of the forming supercontinent laid the groundwork for the subsequent success of later reptile groups, including the dinosaurs themselves. The dominant land vertebrates of the early Permian were the pelycosaurs, a group of synapsids, often referred to as mammal-like reptiles, due to their evolutionary lineage towards mammals. Famous examples include Dimetrodon, characterized by its distinctive sail-like fin on its back. While often depicted as reptiles, pelycosaurs possessed a mix of reptilian and mammalian features. They were diverse in form, ranging from small insect eaters to large carnivores like Dimetrodon, which could reach lengths of several meters. Their sprawling gait, similar to modern lizards, meant they were not particularly agile runners, but they were well suited to traversing the varied landscapes of the early Pangean environment. The sail on Dimetrodon is thought to have played a role in thermoregulation, helping the animal to warm up or cool down by absorbing or radiating heat, a crucial adaptation in a world with significant temperature swings. As the Permian period progressed, pelycosaurs were largely replaced by a more advanced group of synapsids called theropsids. Theropsids were even more mammal-like, exhibiting features such as more upright limbs, differentiated teeth, incisors, canines, molars, and possibly even hair or whiskers in some forms. This group diversified extensively and became the dominant terrestrial vertebrates of the late Permian. Key therapsid groups included the Gorgonopsians, fearsome saber-toothed predators that were the apex carnivores of their time. These creatures were agile and powerful, capable of hunting large prey. Another prominent group was the Dicynodonts, herbivorous therapsids characterized by their turtle-like beaks and often two prominent tusks. Dicynodonts were incredibly successful, ranging from small burrowing forms to large cow-sized grazers, and they were the most abundant large herbivores of the late Permian. Their adaptations for plant eating, such as their beaks for cropping vegetation and powerful jaw muscles, allowed them to exploit the diverse plant life of Pangea. Cynodonts, a specialized group of therapsids, were particularly important as they represent the direct ancestors of mammals. These small to medium-sized animals were often carnivorous or omnivorous, and they exhibited many advanced mammalian traits, including a more efficient chewing mechanism, a secondary palate, allowing them to breathe while chewing, and possibly endothermy or warm-bloodedness. Their increasing sophistication in locomotion and metabolism allowed them to thrive in various niches. While dinosaurs would eventually dominate the large animal roles, cynodonts persisted into the Triassic and Jurassic periods, often as small nocturnal creatures, eventually giving rise to the first true mammals. Alongside the synapsids, various groups of reptiles belonging to the anapsid and diapsid lineages also inhabited Pangea. Anapsids, characterized by a skull with no temporal fenestrae, holes behind the eye socket, included the Prehistoric, large, heavily built herbivores with bony armor plates embedded in their skin. These slow-moving, plant-eating reptiles were common in the late Permian. Diapsids, with two temporal fenestrae, were a more diverse group that would eventually give rise to all modern reptiles, including lizards, snakes, crocodiles, and birds, as well as the extinct dinosaurs and pterosaurs. Early diapsids included small lizard-like forms that were likely insectivorous. During the early Triassic period, following the devastating Permian-Triassic extinction event, the land animal communities underwent a significant restructuring. Many of the dominant Permian therapsids and anapsids either went extinct or suffered severe population declines. This biological vacuum created opportunities for new groups to diversify. Among these were the Archosauromorphs, a group of diapsids that included the ancestors of crocodiles, Terosaurs, and dinosaurs. Early Archosauromorphs were often crocodile-like in appearance, such as the Proterosuchids, which were semi-aquatic predators. Rhynchosaurs, another group of herbivorous diapsids, became very common in the mid-Triassic. These animals had distinctive beaks and broad heads, adapted for cropping tough vegetation. The adaptations of these early land animals to the Pangean environment were crucial for their survival. The sprawling gait of many early reptiles and synapsids, while not as efficient for sustained running as the upright posture of later dinosaurs, provided stability on varied terrain. Their scaly skin helped to prevent water loss, a vital adaptation in the arid Pangean interior. The evolution of the amniotic egg, which allowed reptiles to lay their eggs on land without needing water, was a key innovation that enabled them to fully colonize terrestrial environments, freeing them from a dependency on aquatic habitats for reproduction. This was a significant advantage over amphibians, which still required water for their larval stages. The development of more efficient respiratory and circulatory systems in therapsids also allowed for higher metabolic rates, enabling more active lifestyles. The Permian-Triassic extinction event, the largest mass extinction in Earth's history, dramatically reshaped these terrestrial ecosystems, wiping out many dominant groups and paving the way for the rise of the Archosaurs, including the first true dinosaurs in the mid to late Triassic. The Earth's atmosphere during the time of Pangea, spanning the late Paleozoic and early Mesozoic eras, was a dynamic mixture of gases that profoundly influenced the planet's climate and the evolution of life. The levels of key atmospheric components, particularly oxygen and carbon dioxide, fluctuated significantly during this long period, creating conditions that were often quite different from those of today. Understanding these atmospheric conditions is essential for comprehending the physiology of the animals and plants that inhabited Pangea. In the late Carboniferous period, immediately preceding the full assembly of Pangea, oxygen levels in the atmosphere were exceptionally high, estimated to be around 30 to 35% compared to today's 21%. This superoxygenated atmosphere was largely a result of the extensive burial of organic matter in vast coal swamps. When plant material is buried and prevented from decaying, the carbon within it is sequestered, and the oxygen that would normally be consumed during decomposition is released into the atmosphere. These high oxygen levels are thought to have contributed to the enormous size of some arthropods, such as dragonflies with wingspans of nearly 1 meter, as their respiratory systems, which rely on passive diffusion through tracheae, are more efficient in oxygen-rich environments. As Pangea fully assembled in the Permian period and the climate became more arid, the vast coal swamps of the Carboniferous began to decline. This reduction in organic carbon burial led to a gradual decrease in atmospheric oxygen levels. By the end of the Permian, just before the Permian-Triassic extinction event, oxygen concentrations are estimated to have dropped significantly, possibly to as low as 12 to 15%. This dramatic drop in oxygen, coupled with massive volcanic eruptions in the Siberian traps that released enormous amounts of carbon dioxide and other gases, is considered a major contributing factor to the Permian-Triassic extinction, the largest mass extinction in Earth's history. Such low oxygen levels would have placed severe physiological stress on many terrestrial and marine organisms, making it harder for them to breathe and sustain high metabolic rates. Throughout the Triassic and Jurassic periods, the time when dinosaurs dominated Pangea, atmospheric oxygen levels remained generally lower than modern levels, likely fluctuating between 15 and 20%. While higher than the Permian low, these levels were still below the peak of the Carboniferous. This lower oxygen environment might have influenced the physiology and maximum size of some animals. For instance, the respiratory systems of early dinosaurs, which were more efficient than those of earlier reptiles, may have allowed them to thrive in these conditions. The evolution of bird-like air sacs in some dinosaur lineages, which provide a unidirectional flow of air through the lungs, would have been a significant adaptation for efficient oxygen uptake. Carbon dioxide, CO2 levels in the Pangean atmosphere were generally much higher than today. During the Permian, CO2 concentrations were likely several times higher than pre-industrial levels. This was due to several factors: the reduced burial of organic carbon, less coal formation, and significant volcanic outgassing associated with the formation of Pangea itself and later, the massive eruptions of the Siberian traps. High CO2 levels acted as a powerful greenhouse gas, contributing to a warmer global climate, especially in the Triassic and Jurassic periods. This warmth, combined with the continentality effect of Pangea, led to the widespread arid conditions and extreme temperatures discussed previously. In the Triassic and Jurassic, CO2 levels remained elevated, contributing to a generally warm, ice-free world. There is no evidence of polar ice caps during much of the Mesozoic era. This warm climate, driven by high CO2, allowed for the flourishing of plant life adapted to warmer temperatures, such as cycads and conifers, across broad latitudinal ranges. The high CO2 levels also meant that plants had an abundant supply of carbon for photosynthesis, potentially leading to faster growth rates in some regions. The primary source of atmospheric carbon dioxide during this time was volcanic activity, particularly from mid-ocean ridges and large igneous provinces, which continuously release CO2 into the atmosphere. The weathering of silicate rocks, a process that removes CO2 from the atmosphere, was likely less efficient in the arid interior of Pangea, further contributing to elevated CO2 levels. Nitrogen, N2, was, as it is today, the most abundant gas in the Earth's atmosphere during the Pangean era, comprising roughly 78% of the total. Nitrogen is a relatively inert gas, and its concentration has remained remarkably stable throughout Earth's history, playing a crucial role in diluting oxygen and providing the bulk of atmospheric pressure. Other trace gases, such as methane and water vapour, would also have been present, contributing to the greenhouse effect. The overall atmospheric pressure might have been slightly different from today, but the primary drivers of climate and biological adaptation were the fluctuating levels of oxygen and carbon dioxide. The air they breathed was a fundamental component of the Pangean world, shaping the physiology, distribution, and evolution of all life forms on the supercontinent. Volcanic activity played a profound and pervasive role in shaping the land, atmosphere, and climate of Pangea throughout its existence, from its assembly in the Permian period to its breakup in the Jurassic and Cretaceous. The Earth's internal heat continuously drives plate tectonics, and where these tectonic plates interact, volcanic eruptions are a common consequence. During the time of Pangea, several major volcanic events and sustained periods of volcanism released immense quantities of lava, ash, and gases, leaving an indelible mark on the supercontinent's geography and influencing global environmental conditions. One of the most significant volcanic events associated with Pangea occurred at the very end of the Permian period, approximately 252 million years ago. This was the eruption of the Siberian Traps, a vast, large, igneous province located in what is now Siberia. These eruptions were not single events, but a series of massive, prolonged volcanic outbursts that lasted for hundreds of thousands of years. They involved the outpouring of enormous volumes of basaltic lava, covering an area of over 2 million square kilometers, forming thick layers of volcanic rock. The sheer scale of the Siberian Traps eruptions released colossal amounts of greenhouse gases, including carbon dioxide and methane, into the atmosphere. This rapid and sustained increase in atmospheric carbon dioxide led to a dramatic rise in global temperatures, causing widespread ocean acidification and anoxia, lack of oxygen, in the oceans. The environmental devastation caused by the Siberian Traps volcanism is widely considered the primary trigger for the Permian Triassic extinction event, the most severe mass extinction in Earth's history, which wiped out over 90% of marine species and 70% of terrestrial vertebrate species. The formation of Pangea itself was accompanied by extensive volcanism along its active margins. As continental plates collided to form the supercontinent, subduction zones developed where oceanic crust was forced beneath the overriding continental plates. This process melted the descending oceanic crust, generating magma that rose to the surface, leading to the formation of volcanic arcs. For instance, the collision that formed the Appalachian Mountains and the Hercynian Belt in Europe involved significant periods of volcanic activity. These volcanoes would have contributed to the rugged topography of the newly formed mountain ranges, adding volcanic peaks and plateaus to the landscape. While these were not on the scale of the Siberian Traps, their cumulative effect over millions of years contributed to the atmospheric gas composition and regional environmental conditions. During the Triassic period, as life slowly recovered from the Permian extinction and dinosaurs began to emerge, volcanic activity continued. Although no single event matched the scale of the Siberian Traps, rifting and localized volcanism occurred as stresses built up within the supercontinent. These eruptions would have released more gases, contributing to the generally warm and high carbon dioxide atmosphere of the Triassic. The lava flows and ash deposits from these volcanoes would have altered local landscapes, creating new rock formations and influencing soil composition. The ash could also have temporarily blocked sunlight, causing short-term cooling events, but the overall long-term effect of sustained volcanism was warming due to greenhouse gas emissions. The most widespread and impactful volcanic activity during the Mesozoic era, after the initial formation of Pangea, was associated with its breakup. As Pangea began to rift apart in the Jurassic period, large volumes of magma rose from the mantle, leading to the formation of vast flood basalts. The most prominent example is the Central Atlantic Magmatic Province, or CAMP, which erupted around 200 million years ago, coinciding with the Triassic-Jurassic extinction event. This massive outpouring of lava and release of gases is implicated as a major cause of this extinction, which paved the way for the full dominance of dinosaurs in the Jurassic. The CAMP eruptions marked the initial stages of the opening of the Atlantic Ocean, as magma rose along the newly forming rift zones, creating new oceanic crust and separating the continents. These eruptions would have created extensive volcanic plateaus and coastlines, characterized by basaltic cliffs and lava flows. Throughout the Jurassic and Cretaceous periods, as the continents continued to drift apart, volcanism remained active along the spreading centers of the newly forming ocean basins. Mid-ocean ridges, where new oceanic crust is continuously generated, are sites of constant, though generally effusive, volcanic activity. While these underwater eruptions did not directly impact the land surface of the continents, they continuously released gases into the ocean and atmosphere, contributing to the global carbon cycle and influencing ocean chemistry. On the continental margins, subduction zones continued to generate volcanic arcs, such as those that would eventually form the Andes Mountains as South America drifted westward. These volcanoes shaped regional landscapes, creating fertile volcanic soils in some areas and posing hazards to local ecosystems. The geological record of Pangea is replete with evidence of this extensive volcanism. Thick layers of basaltic rock known as flood basalts are found on continents that were once connected, such as the Deccan Traps in India, though these are later Cretaceous in age, and the Karoo-Farrar large igneous province in southern Africa and Antarctica, which erupted during the Jurassic and is linked to the breakup of Gondwana. Layers of volcanic ash are preserved in sedimentary rock sequences, providing valuable chronological markers and insights into past atmospheric conditions. The presence of these volcanic rocks and their associated mineral deposits provides direct evidence of the Earth's dynamic internal processes shaping the supercontinent and its environment. Volcanism was not just a geological phenomenon, it was a powerful environmental modifier, influencing atmospheric composition, global temperatures, ocean chemistry, and ultimately the trajectory of life on Earth during the age of Pangea. The rise of dinosaurs to global dominance was not a sudden event, but a gradual process that unfolded over tens of millions of years during the Triassic period, following the most devastating mass extinction in Earth's history. To understand what made dinosaurs unique and how they came to rule the land, it is crucial to examine the environmental context and the evolutionary innovations that set them apart from their predecessors. The Permian-Triassic extinction event, around 252 million years ago, cleared the ecological stage, removing many of the dominant land animals of the Permian and creating vacant niches that new groups could exploit. Before the dinosaurs, the terrestrial ecosystems of the late Permian and early Triassic were dominated by various groups of synapsids, often referred to as mammal-like reptiles, such as the dicynodonts and gorgonopsians, and large anapsids like the Prehistorics. These animals were successful in their time, but the Permian extinction severely curtailed their diversity and abundance. In the immediate aftermath of the extinction, the early Triassic saw a period of ecological recovery, with a relatively low diversity of surviving species. This is often referred to as the disaster fauna, or recovery interval, characterized by widespread generalist species. Among the survivors were early archosauromorphs, a group of diapsid reptiles that included the ancestors of crocodiles, Terosaurs, and dinosaurs. The first true dinosaurs appeared in the mid-Triassic period, approximately 230 million years ago, in what is now South America. These early dinosaurs were relatively small, bipedal, and carnivorous. Examples include Eoraptor and Herrerasaurus. They were not initially dominant and lived alongside a diverse array of other reptiles, including various groups of archosauromorphs that were more numerous and often larger. These non-dinosaurian archosauromorphs included the Cretaceans, a group that gave rise to modern crocodiles and their extinct relatives, such as the large quadrupedal Rauisuchians and Etosaurs. For a significant portion of the Triassic, these Cretaceans were the apex predators and large herbivores, outcompeting the early dinosaurs in many ecosystems. What made dinosaurs unique and ultimately allowed them to outcompete other groups? Several key anatomical features and physiological advantages are thought to have played a role. One of the most significant was their posture. Early dinosaurs evolved a more upright parasagittal limb posture, meaning their legs were positioned directly underneath their bodies, rather than sprawling out to the sides like lizards or crocodiles. This upright stance provided several benefits. It allowed for more efficient locomotion, enabling sustained running and greater agility. It supported greater body weight, paving the way for the evolution of giant forms, and it allowed for more efficient breathing during movement, as the lungs were not compressed by the movement of the limbs, unlike in sprawling reptiles. This efficient locomotion was a crucial advantage in hunting prey or escaping predators, especially in a world where many other large animals still had a sprawling gait. Another important factor was their respiratory system. While direct evidence is scarce, it is believed that early dinosaurs, and certainly their later descendants, developed a more efficient respiratory system, possibly involving air sacs similar to those found in modern birds, which are direct descendants of dinosaurs. This system allows for a unidirectional flow of air through the lungs, ensuring a continuous supply of fresh, oxygen-rich air and more efficient oxygen extraction. This would have been a significant advantage in the generally lower oxygen atmosphere of the Triassic and Jurassic periods, allowing dinosaurs to maintain higher metabolic rates and more active lifestyles than many of their contemporaries. Their skeletal structure also exhibited unique features. Dinosaurs possessed a perforated acetabulum, a hole in the hip socket, which allowed for the upright posture of their legs. Their ankle joints also had a unique structure that provided stability during locomotion. These skeletal adaptations provided a robust and efficient framework for movement and support. Furthermore, many early dinosaurs were relatively fast and agile, which would have given them an edge in hunting and evading predators in the recovering Triassic ecosystems. The Triassic-Jurassic extinction event, around 200 million years ago, played a pivotal role in the final ascendancy of dinosaurs. While not as severe as the Permian extinction, this event caused significant ecological disruption, leading to the extinction of many large crurotarsans and other non-dinosaurian archosauromorphs that had previously dominated the large animal niches. The exact cause of this extinction is debated, but massive volcanic eruptions associated with the Central Atlantic Magmatic Province, CAP, are strongly implicated. These eruptions released large amounts of greenhouse gases, causing rapid climate change and ocean acidification. With many of their competitors removed, dinosaurs were well positioned to diversify rapidly and fill these vacant ecological roles. Following the Triassic-Jurassic extinction, dinosaurs underwent a rapid evolutionary radiation in the early Jurassic period. They diversified into a wide array of forms, including the first true giant sauropods, long-necked herbivores, and a greater variety of theropods, carnivores. Their unique anatomical and physiological adaptations, combined with the ecological opportunities created by the two major extinction events, allowed them to expand their geographical range across Pangea and evolve into the dominant terrestrial vertebrates for the next 135 million years. Their upright posture, efficient respiration, and robust skeletal structure provided the evolutionary blueprint for the incredible diversity and immense sizes that would characterize the dinosaur age. The Triassic period, spanning from approximately 252 million to 200 million years ago, represents the dawn of the dinosaur age. While the Jurassic and Cretaceous periods are famous for their colossal and iconic dinosaurs, the Triassic was a time of smaller, more modest forms, and a period when dinosaurs were still finding their ecological footing amidst a diverse array of other reptiles. The Triassic environment, shaped by the supercontinent Pangea and the recovery from the Permian-Triassic extinction, presented unique challenges and opportunities for these early dinosaurs. In the immediate aftermath of the Permian-Triassic extinction event, the early Triassic was a time of ecological recovery. The dominant land animals were not dinosaurs but rather surviving groups of synapsids, mammal-like reptiles, like Lystrosaurus, and various early archosauromorphs. The first true dinosaurs appeared in the mid-Triassic, around 230 million years ago. These earliest dinosaurs were generally small, bipedal and carnivorous. They were not the giants that would later roam the Earth, and they were far from the dominant land animals. One of the earliest and best-known Triassic dinosaurs is Eoraptor, discovered in Argentina. Eoraptor was a small, agile bipedal carnivore, measuring only about 1 meter in length. Its teeth suggest a diet of small animals. Another early dinosaur from the same region is Herbivorous, which was larger than Eoraptor, reaching up to 6 meters in length, and was also a bipedal carnivore. These early forms already exhibited the key dinosaurian features, such as the upright limb posture, which distinguished them from other sprawling reptiles. Their presence in what is now South America suggests that this region, then part of the southern supercontinent Gondwana, was a key evolutionary cradle for the earliest dinosaurs. As the Triassic progressed into its late stages, dinosaurs began to diversify, though they still remained less numerous and often smaller than other large reptiles. the late Triassic saw the emergence of several distinct dinosaur lineages. Among the earliest large herbivores were the prosauropods. These were long-necked, often bipedal or facultatively quadrupedal, meaning they could walk on 2 or 4 legs, dinosaurs that were ancestors to the giant sauropods of the Jurassic. Examples include Plateosaurus, which could reach lengths of up to 10 meters. Prosauropods were successful plant eaters, using their long necks to browse on high vegetation. Their teeth were adapted for processing plant material, and their digestive systems were capable of breaking down tough plant fibers. Carnivorous dinosaurs of the late Triassic were primarily small to medium-sized theropods. These were bipedal predators with sharp teeth and claws, adapted for hunting other animals. Chelophysis, a slender, agile theropod from North America, is a well-known example, reaching about 3 meters in length. Fossils of Chelophysis have been found in large bone beds, suggesting they may have lived in groups. Another important group of late Triassic theropods were the Ceratosaurs, which included species like Dilophosaurus, known for the 2 crests on its head. While often depicted as large, Dilophosaurus was a medium-sized predator, reaching around 6 meters. These theropods were the primary large predators in many Triassic ecosystems, preying on other dinosaurs, early mammals, and various reptiles. Beyond the early sauropodomorphs and theropods, other dinosaur groups also made their first appearance in the late Triassic. Early ornithischians, the bird-hipped dinosaurs, also began to emerge. These were generally small bipedal herbivores, such as Lesothosaurus. They possessed a unique pelvic structure that allowed for efficient processing of plant material. While not as diverse or prominent as the sauropodomorphs and theropods in the Triassic, their appearance marked the beginning of a lineage that would later include famous dinosaurs like Triceratops and Stegosaurus. Despite the diversification of dinosaurs, they were not the undisputed rulers of the Triassic world. Other reptile groups, particularly the Crurotarsans, a group that includes the ancestors of modern crocodiles, were often more numerous and ecologically dominant. Large Rauisuchians, such as Postosuchus, were formidable quadrupedal predators that often outcompeted early theropods for top predator roles. Etosaurs, heavily armoured, herbivorous Crurotarsans, were common large plant eaters. Phytosaurs, crocodile-like aquatic predators, dominated river and lake environments. These non-dinosaurian archosauromorphs were highly successful throughout much of the Triassic, and dinosaurs coexisted with them, often occupying smaller niches. The Triassic-Jurassic extinction event, around 200 million years ago, marked a turning point. This extinction selectively affected many of the Crurotarsan groups, including the large Rauisuchians and Phytosaurs, as well as many large amphibians and some mammal-like reptiles. Dinosaurs, perhaps due to their more efficient physiology, upright posture, or simply luck, were less severely impacted. This event cleared the ecological stage, removing many of their primary competitors and opening up numerous large animal niches. This ecological vacuum allowed dinosaurs to undergo a rapid and explosive diversification in the early Jurassic, leading to their eventual global dominance and the evolution of the much larger and more specialized forms that characterized the Middle and Late Mesozoic era. The Triassic period, therefore, was the crucial proving ground for dinosaurs, a time of humble beginnings and gradual diversification, setting the stage for their spectacular rise. The Jurassic period, spanning from approximately 200 million to 145 million years ago, marked a pivotal era in the history of dinosaurs, characterized by the emergence of truly colossal forms that became the dominant terrestrial animals on Earth. This middle period of the Mesozoic era saw the supercontinent Pangea beginning its slow process of fragmentation, which, while eventually leading to continental separation, still allowed for a relatively uniform global distribution of many dinosaur groups. The lush vegetation and generally warm, humid climate of the Jurassic provided the ideal conditions for the evolution and proliferation of these enormous creatures. The most iconic and massive dinosaurs of the Jurassic were the sauropods, the long-necked, long-tailed quadrupedal herbivores. These gentle giants reached unprecedented sizes, becoming the largest land animals to have ever lived. Their immense bulk was supported by pillar-like legs, and their long necks allowed them to browse on high foliage, reaching leaves that other herbivores could not. Different sauropod lineages evolved diverse feeding strategies. Diplodocids, such as Diplodocus and Apatosaurus, possessed relatively slender whip-like tails and peg-like teeth, suggesting they stripped leaves from branches. Diplodocus, for instance, could reach lengths of over 25 meters, with its neck alone accounting for a significant portion of its body. Apatosaurus, though slightly shorter, was more robustly built. Both were widespread across North America during the late Jurassic. Another prominent group of sauropods were the macronarians, which included Brachiosaurus and Camarasaurus. Brachiosaurus, known for its exceptionally long front legs that made its shoulders higher than its hips, could reach heights of up to 13 meters, allowing it to browse on the very tops of tall conifer trees. Its teeth were broader and spoon-shaped, suitable for cropping tougher vegetation. Camarasaurus, a more common and somewhat smaller macronarian, had a distinctive box-like skull and robust teeth, indicating a diet of coarser plant material. These sauropods were not only massive but also highly successful, adapting to various environments across Pangea. Their enormous size was a primary defense against predators, and their sheer numbers indicate a thriving ecosystem capable of supporting such immense biomass. The ability of sauropods to grow to such sizes was facilitated by their efficient bird-like respiratory systems, which allowed them to take in large amounts of oxygen, and their relatively simple digestive systems, which likely relied on fermentation to break down tough plant matter. The abundance of these giant herbivores naturally led to the evolution of equally formidable carnivorous dinosaurs. The large meat-eaters of the Jurassic were primarily theropods, bipedal predators that evolved to hunt the massive sauropods and other large herbivores. Allosaurus was one of the most common and successful large theropods of the late Jurassic, particularly in North America. Reaching lengths of up to 12 meters, Allosaurus was a powerful predator with a robust skull, serrated teeth, and strong claws on its three-fingered hands. Evidence from fossil bone beds suggests that Allosaurus may have hunted in groups, which would have enabled them to take down even the larger sauropods. Its hunting strategy likely involved ambush and powerful slashing bites, rather than a sustained struggle, using its strong neck muscles to deliver rapid, deep wounds. Other significant Jurassic theropods included Ceratosaurus, recognizable by the prominent horn on its snout and a row of bony plates along its back. Ceratosaurus was slightly smaller than Allosaurus, typically around 6 to 8 meters long, and likely preyed on medium-sized dinosaurs. Megalosaurus, one of the first dinosaurs ever formally described, was a large theropod from Europe, also active during the Middle to Late Jurassic. These large predators occupied the apex of the food chain, controlling the populations of the vast herbivore herds. Their sharp senses, powerful jaws, and swift movements for their size made them formidable hunters in the Jurassic landscape. The global spread of these Jurassic giants was facilitated by the continued connection of Pangea. While rifting had begun, particularly in the central Atlantic region, the land bridges between the major continental blocks remained largely intact for much of the Jurassic. This allowed sauropods and large theropods to disperse across vast geographical areas. For example, similar sauropod and theropod genera are found in fossil sites in North America, Europe, Africa, and South America, indicating a relatively free exchange of species across the supercontinent. The widespread distribution of a lush conifer forests, cycads, and ferns provided a continuous food source for herbivores, which in turn supported the large carnivores. The warm, humid climate across much of Pangea during the Jurassic, with ample rainfall in many regions, allowed for the growth of the immense plant biomass necessary to sustain these enormous animals. Beyond the sauropods and large theropods, the Jurassic also saw the diversification of other dinosaur groups. Stegosaurus, a distinctive armoured dinosaur with large bony plates along its back and a spiked tail, was a common herbivore in the late Jurassic of North America. Its unique defensive adaptations made it a challenging prey for predators. Early ornithopods, a group of bipedal herbivores, also began to diversify, though they would become far more prominent in the Cretaceous. Small, agile theropods, such as Compsognathus, also inhabited the Jurassic world, preying on small vertebrates and insects. The first birds, such as Archaeopteryx, also emerged in the late Jurassic, evolving from small feathered theropods, marking a significant evolutionary milestone. The Jurassic period was truly the age of giants, a time when dinosaurs reached their peak in terms of sheer size and established their dominance over terrestrial ecosystems across the unified landmass of Pangea. The Cretaceous period, spanning from approximately 145 million to 66 million years ago, represents the final and most diverse chapter of the dinosaur age, often referred to as its climax. This period witnessed an incredible radiation of dinosaur forms, the rise of flowering plants, and significant geological changes as Pangea continued its breakup, leading to the formation of continents much closer to their modern positions. The increasing continental isolation fostered greater regional diversity among dinosaur species, culminating in the appearance of some of the most famous and specialized dinosaurs. One of the most iconic dinosaurs of the late Cretaceous was Tyrannosaurus rex, a massive carnivorous theropod that roamed North America. Reaching lengths of up to 13 meters and weighing several tons, Tyrannosaurus rex possessed one of the most powerful bites of any land animal, capable of crushing bone. Its large, serrated, banana-shaped teeth were designed for tearing flesh and breaking bones. While its arms were remarkably small, they were surprisingly strong, possibly used to hold struggling prey close. Debate continues among scientists regarding whether Tyrannosaurus rex was primarily an active predator or a scavenger, but evidence suggests it was likely both, an opportunistic feeder capable of hunting large prey. Its powerful legs indicate it could move at considerable speeds, making it a formidable hunter in its ecosystem. Coexisting with Tyrannosaurus rex in North America was Triceratops, a large quadrupedal herbivore belonging to the Ceratopsian group. Triceratops is instantly recognizable by its 3 facial horns and a large bony frill that protected its neck. These features were likely used for defense against predators like Tyrannosaurus rex, as well as for display within its own species. Triceratops possessed a powerful beak-like mouth and rows of shearing teeth, perfectly adapted for cropping tough fibrous plants. Fossil evidence suggests that Triceratops may have lived in herds, providing mutual protection and possibly engaging in head-to-head combat for dominance, similar to modern rhinos or cattle. The Cretaceous saw the widespread diversification of ornithopods, particularly the hadrosaurs, or duck-billed dinosaurs. These highly successful herbivores became incredibly abundant, especially in North America and Asia. Hadrosaurs, such as Edmontosaurus and Parasaurolophus, possessed thousands of small grinding teeth arranged in dental batteries, allowing them to efficiently process tough plant material. Many hadrosaurs also featured elaborate crests on their heads, which are thought to have been used for visual display or for producing distinct sounds for communication within their herds. Their ability to walk on 2 legs or 4, combined with their efficient feeding apparatus, made them highly adaptable and successful grazers. Another prominent group of Cretaceous dinosaurs were the ankylosaurs, heavily armoured quadrupedal herbivores. Dinosaurs like Ankylosaurus were essentially living tanks, covered in thick, bony plates, and often possessing a massive bony club at the end of their tails. This formidable armour provided excellent protection against large predators. Pachycephalosaurs, characterised by their thick dome-shaped skulls, were another unique group of herbivores. Their domes are thought to have been used in head-butting contests, possibly for mating rights or territorial disputes. The Cretaceous also saw the continued evolution and diversification of smaller, agile carnivorous theropods, particularly the dromaeosaurids, often referred to as raptors. Velociraptor from Asia, though much smaller than often depicted in popular culture, about 2 meters long, was a swift and intelligent predator with a distinctive sickle-shaped claw on each foot, likely used for subduing prey. Larger dromaeosaurids, such as Deinonychus from North America, were more substantial and may have hunted in packs, allowing them to tackle prey larger than themselves. Other notable Cretaceous theropods included Spinosaurus, a massive sail-backed fish-eating dinosaur from Africa, and Giganotosaurus, a colossal predator from South America that rivaled Tyrannosaurus rex in size. A significant biological revolution of the Cretaceous was the rapid rise and diversification of flowering plants, or angiosperms. While gymnosperms, conifers, cycads, ginkgos, had dominated the Jurassic, angiosperms began to spread rapidly in the Cretaceous, eventually becoming the dominant plant life. This had a profound impact on herbivorous dinosaurs, leading to the evolution of new feeding adaptations, such as the dental batteries of hadrosaurs, to process these new types of plants. The co-evolution between flowering plants and pollinating insects also intensified, contributing to the overall increase in biodiversity. The breakup of Pangea, which began in the Jurassic, accelerated during the Cretaceous. The continents drifted further apart, leading to the formation of new ocean basins and the isolation of land masses. This continental drift played a crucial role in the diversification of dinosaurs, as populations became geographically separated, leading to the evolution of unique species on different continents. For example, while tyrannosaurids were dominant in North America and Asia, abelisaurids, a different group of large theropods, were the apex predators in South America, Africa, and India. This regional endemism contributed to the incredible variety of dinosaur forms seen in the late Cretaceous. The period concluded with the catastrophic asteroid impact 66 million years ago, leading to the mass extinction that ended the reign of the non-avian dinosaurs. Carnivorous dinosaurs, scientifically known as theropods, were the dominant predators of terrestrial ecosystems throughout the Mesozoic era, from their origins in the Triassic period to their ultimate demise at the end of the Cretaceous. The term theropod means beastfoot, referring to their characteristic three-toed feet, usually equipped with sharp claws. These dinosaurs were almost universally bipedal, walking on two legs, which freed their forelimbs for grasping prey, balance, or other specialized functions. Their adaptations for a predatory lifestyle were diverse and highly effective, allowing them to occupy the apex of the food chain in nearly every environment they inhabited. The earliest theropods, emerging in the mid-Triassic period, were relatively small and agile. Dinosaurs like Euraptor and Herbivorous, from what is now South America, were bipedal hunters typically ranging from 1 to 6 meters in length. They possessed sharp, serrated teeth, ideal for slicing flesh. Their slender builds and long legs suggest they were swift runners, capable of pursuing and ambushing smaller prey such as early reptiles and amphibians. These early meat-eaters established the basic body plan that would be refined and scaled up in later theropod lineages. Their hunting strategies likely involved a combination of pursuit and a quick, decisive bite to incapacitate their victims. As the Jurassic period unfolded, theropods evolved into much larger and more powerful forms. Allosaurus, a prominent predator of the late Jurassic in North America and Europe, exemplified the robust, large-bodied theropod. Reaching lengths of up to 12 meters, Allosaurus had a massive skull with powerful jaws and numerous recurved, serrated teeth, perfect for tearing through the flesh of large herbivores. Its forelimbs, though relatively short compared to its body, were strong and equipped with 3 sharp claws, likely used to grasp and hold struggling prey. Evidence from fossil bone beds, where multiple Allosaurus skeletons are found alongside large herbivore remains, suggests that these predators may have hunted in groups, allowing them to take down enormous sauropods. Their hunting technique likely involved powerful slashing bites to inflict severe wounds, leading to blood loss and eventual collapse of the prey. Other Jurassic theropods like Ceratosaurus, with its distinctive nasal horn and bony plates, were also formidable predators, though typically smaller than Allosaurus. These mid-sized carnivores likely targeted medium-sized dinosaurs and other vertebrates. Megalosaurus, an early large theropod from Europe, also showcased the general adaptations for meat-eating. Strong jaws, sharp teeth, and powerful hind limbs for locomotion and striking. The success of these Jurassic meat-eaters was directly linked to the abundance of large herbivorous dinosaurs, particularly the sauropods, which provided an ample food source for these apex predators. The Cretaceous period saw the greatest diversity and specialization among meat-eating dinosaurs. Tyrannosaurus rex from North America and Asia is perhaps the most famous. Its massive skull, disproportionately large teeth, and incredible bite force, estimated to be the strongest of any terrestrial animal, indicate its specialization in crushing bone and tearing through flesh. While its small forelimbs remain a subject of debate, its powerful hind legs suggest it was capable of bursts of speed. Whether it was an active hunter, a scavenger, or both, Tyrannosaurus rex was undoubtedly the apex predator of its ecosystem. Other colossal Cretaceous theropods included Giganotosaurus from South America and Carcharodontosaurus from Africa. These dinosaurs rivaled Tyrannosaurus rex in size, reaching lengths of 13 meters or more. They possessed long, blade-like serrated teeth, suggesting a primary strategy of inflicting deep, wide wounds to cause massive blood loss in their large herbivorous prey, rather than bone crushing. Spinosaurus, also from Africa, presented a unique adaptation among large theropods. With its distinctive neural spine sail and elongated, crocodile-like snout filled with conical teeth, Spinosaurus was primarily a piscivore, or fish-eater. Its adaptations, including dense bones for buoyancy control and powerful forelimbs, suggest a semi-aquatic lifestyle, hunting large fish and other aquatic prey in river systems. Smaller, more agile theropods also thrived in the Cretaceous. The dromaeosaurids, commonly known as raptors, such as Velociraptor from Asia and Deinonychus from North America, were characterized by their large, retractable sickle-shaped claw on the second toe of each foot. These highly intelligent and swift predators likely hunted in packs, overwhelming prey much larger than themselves. Their keen senses, powerful legs, and grasping claws made them efficient killing machines. Other specialized Cretaceous theropods included Carnotaurus from South America, known for its short, blunt horns above its eyes and exceptionally robust legs, indicating bursts of speed. The teeth of theropods were a key adaptation for their carnivorous diet. Most possessed sharp, blade-like teeth that were often serrated, like a steak knife, to efficiently slice through flesh. These teeth were continuously replaced throughout the dinosaur's life. Their powerful jaw muscles allowed for a strong bite force, and their skulls were often kinetic, meaning they had flexible joints that allowed the jaws to absorb stress and manipulate prey. Claws on both hands and feet were also crucial tools for subduing and dismembering prey. The evolution of meat-eating dinosaurs was a continuous process of refinement, leading to a wide array of specialized hunters, each adapted to exploit particular niches and prey types within the diverse ecosystems of Pangea and its fragmenting continents. Herbivorous dinosaurs, those that subsisted entirely on plant matter, constituted the vast majority of dinosaur species and formed the foundational base of the Mesozoic food web. Their evolution was marked by an incredible array of unique adaptations for processing diverse plant materials, from tough conifer needles to softer ferns and later, flowering plants. These adaptations included specialized teeth, powerful jaws, and complex digestive systems. Furthermore, given their role as primary prey for large carnivorous dinosaurs, plant eaters also developed a remarkable diversity of defensive features, ranging from immense size to elaborate armor and weaponry. The most iconic of the plant-eating dinosaurs were the sauropods, the long-necked quadrupedal giants that dominated the Jurassic and continued into the Cretaceous. Their sheer size, often exceeding 25 meters in length and weighing many tens of tons, was their primary defense against predators. A full-grown sauropod such as Brachiosaurus or Diplodocus would have been nearly invulnerable to even the largest theropods. Their long necks, supported by a series of hollow air sac-filled vertebrae, allowed them to reach high into the canopies of conifer trees, browsing on leaves and shoots that were inaccessible to other herbivores. Different sauropod groups had distinct dental adaptations. Diplodocids, like Diplodocus, possessed peg-like teeth at the front of their mouths, suitable for stripping leaves from branches. Macronarians, such as Brachiosaurus, had broader spoon-shaped teeth, indicating they cropped more substantial vegetation. Sauropods likely swallowed large quantities of plant material with minimal chewing, relying on gastroliths, or stomach stones, in their gizzards to grind down tough plant fibers, similar to modern birds. Their massive digestive tracts, which would have housed extensive fermentation chambers, were essential for extracting nutrients from their fibrous diet. Another major group of plant-eating dinosaurs were the ornithischians, characterized by their bird-hipped pelvic structure, which allowed for more efficient processing of plant material. This group included a wide variety of forms, each with unique feeding and defensive specializations. The stegosaurs, such as Stegosaurus from the late Jurassic, were medium to large-sized quadrupeds with distinctive bony plates along their backs and a spiked tail known as a thagomizer. These plates may have served for display, thermoregulation, or passive defense, while the tail spikes were undoubtedly used as an active weapon against predators like Allosaurus. Stegosaurs had small leaf-shaped teeth and a relatively weak bite, suggesting they fed on low-lying, softer vegetation. Their digestive process likely involved a gizzard, similar to sauropods. Ankylosaurs, prominent in the Cretaceous, were the armoured tanks of the dinosaur world. Dinosaurs like Ankylosaurus were heavily built quadrupeds, covered from head to tail in thick, bony plates and often adorned with spikes. Some ankylosaurs, like Ankylosaurus itself, possessed a massive bony club at the end of their tails, a powerful weapon capable of inflicting serious damage on a predator. Their broad, flat teeth and wide muzzles suggest they were non-selective grazers, consuming large quantities of low-lying vegetation. Their robust bodies and low centre of gravity made them difficult to overturn, and their armour provided excellent passive defence. Ceratopsians, or horned dinosaurs, were another highly successful group of ornithischians that flourished in the late Cretaceous, particularly in North America and Asia. Triceratops is the most famous example, with its 3 facial horns and a large bony frill protecting its neck. These horns and frills were likely used for both defense against predators like Tyrannosaurus rex and for intraspecific combat, such as sparring for mating rights or territory. Ceratopsians possessed a powerful parrot-like beak at the front of their mouths for cropping tough vegetation, backed by rows of shearing teeth that formed a dental battery, allowing them to slice and grind fibrous plants efficiently. Their strong jaw muscles enabled a powerful bite, making them highly effective at processing a wide range of plant materials. Hadrosaurs, or duck-billed dinosaurs, were among the most abundant and diverse herbivores of the late Cretaceous. These ornithopods were highly specialized plant eaters, known for their unique dental batteries, which consisted of hundreds of tightly packed, continuously replaced teeth that formed a grinding surface. This allowed them to process tough, fibrous plant material, including the newly evolving flowering plants, with remarkable efficiency. Hadrosaurs could walk on all fours, but were also capable of bipedal locomotion, perhaps for faster movement or reaching higher branches. Many hadrosaurs possessed elaborate crests on their heads, which are thought to have been used for visual display, species recognition, or for producing distinct vocalizations for communication within their herds. Their sheer numbers and widespread distribution suggest they were highly successful grazers, forming large herds that migrated across the landscape. Other ornithopods, such as Iguanodon from the early Cretaceous, were large, bipedal or facultatively quadrupedal herbivores with distinctive thumb spikes, possibly used for defense or stripping vegetation. Small, agile ornithopods like Hypsilophodon were also present, likely feeding on softer ground vegetation. The evolution of these diverse plant-eating dinosaurs was closely tied to the evolution of plant life itself. Early dinosaurs fed primarily on gymnosperms, conifers, cycads, ginkgos, and spore-bearing plants, ferns, horsetails. The rise of flowering plants in the Cretaceous provided new food sources, driving further specialization in herbivore dentition and digestive systems. The intricate relationship between plant eaters and the vegetation they consumed was a fundamental driver of Mesozoic terrestrial ecosystem dynamics. Pterosaurs were a unique and diverse group of flying reptiles that soared through the skies alongside dinosaurs for over 150 million years, from the late Triassic to the end of the Cretaceous period. Despite popular misconception, pterosaurs were not dinosaurs, nor were they birds or bats. They represented a distinct lineage of archosaurs, closely related to dinosaurs, but evolving their own specialized adaptations for powered flight. Their mastery of the air allowed them to exploit ecological niches unavailable to terrestrial vertebrates, ranging from fishing over ancient seas to soaring over the supercontinent Pangea. The most striking feature of pterosaurs was their wings. Unlike birds, which use feathers, or bats, which use skin stretched between elongated fingers, pterosaur wings were formed by a membrane of skin and muscle, called the patagium, that stretched from an enormously elongated fourth finger to their ankles. This wing finger was highly specialized, consisting of several long, slender bones that provided support and flexibility. The rest of their hand bones were relatively small, with 3 clawed fingers that were free for grasping or climbing. The wing membrane itself was complex, likely reinforced by internal fibers and capable of subtle shape changes to control flight. This unique wing structure allowed for efficient soaring and flapping flight, enabling pterosaurs to cover vast distances. Pterosaurs exhibited an astonishing range of sizes. The earliest pterosaurs, appearing in the late Triassic, were generally small, often no larger than modern sparrows, with wingspans of less than 1 meter. Examples include Eudimorphodon and Preondactylus. These early forms likely hunted insects or small vertebrates. As they evolved, their sizes increased dramatically. Jurassic pterosaurs such as Rhamphorhynchus had long, bony tails often tipped with a rudder-like vein and sharp teeth, suggesting a diet of fish. Pterodactylus, another Jurassic form, was one of the first short-tailed pterosaurs, hinting at the diversity that would follow. The Cretaceous period saw the largest pterosaurs, truly gigantic flyers that dominated the skies. Quetzalcoatlus from North America was one of the largest known flying animals of all time, with a wingspan estimated to be 10 to 11 meters, comparable to a small airplane. Despite its immense size, Quetzalcoatlus was lightly built with hollow bones, similar to birds, to reduce weight for flight. Its long, toothless beak suggests a varied diet, possibly including scavenging carcasses, preying on small terrestrial animals, or even filter feeding. Another large Cretaceous pterosaur was Pteranodon, famous for its distinctive cranial crest. Pteranodon was a skilled glider, with a wingspan of up to 7 meters, and its fossil remains are often found in marine deposits, indicating it was primarily a fish-eater, snatching prey from the ocean surface. Pterosaurs possessed several other adaptations for flight. Their bones were hollow and filled with air sacs, extending from their respiratory system, which made their skeletons remarkably lightweight yet strong. This system also contributed to a highly efficient respiratory system, similar to that of birds, allowing for high metabolic rates necessary for powered flight. Evidence from fossil impressions suggests that many pterosaurs had a fur-like covering called pycnofibers, which would have provided insulation, indicating that they were likely warm-blooded or endothermic, capable of generating their own body heat. This warm-bloodedness would have been essential for sustaining the energy demands of flight. While primarily aerial, pterosaurs were also capable of terrestrial locomotion. Fossil trackways indicate that they walked on all fours, using their folded wings as forelimbs, giving them a somewhat awkward but effective gait on the ground. Some larger forms, like Quetzalcoatlus, may have been capable of powerful launches from the ground using their strong hind legs and forelimbs, propelling themselves into the air. Their ability to walk on land allowed them to access terrestrial food sources and nesting sites. Pterosaurs occupied a wide range of ecological niches. Many were piscivores, specializing in catching fish from the surface of lakes and oceans. Others were insectivores, snatching insects from the air or ground. Some larger forms may have been generalist predators or scavengers, feeding on small vertebrates or carrion. Their global distribution across Pangea and its fragmenting continents demonstrates their adaptability to diverse environments. The evolution of pterosaurs represents a remarkable example of convergent evolution, where different lineages independently evolve similar solutions to the challenge of flight. They dominated the skies for millions of years before eventually being outcompeted by the rapidly diversifying birds in the late Cretaceous, though some large forms persisted until the very end of the Mesozoic era. While dinosaurs ruled the land, the vast ocean surrounding Pangea, particularly the immense Panthalassa Ocean and the warm Tethys Sea, were home to a spectacular array of large marine reptiles. These creatures were not dinosaurs, but rather distinct lineages of reptiles that had returned to the sea, evolving remarkable adaptations for an aquatic existence. Their evolution and diversification spanned the entire Mesozoic era, filling various ecological niches as apex predators, fish-eaters, and mollusk crushers. One of the earliest and most fish-like groups of marine reptiles were the ichthyosaurs, meaning fish lizards. These highly specialized predators emerged in the early Triassic, and reached their peak diversity in the Jurassic period. Ichthyosaurs evolved a remarkably streamlined torpedo-shaped body, convergent with modern dolphins and tuna, allowing for efficient movement through water. They possessed a large crescent-shaped tail fluke, similar to that of fish and whales for powerful propulsion. Their limbs had transformed into paddle-like flippers, used for steering and stability. Ichthyosaurs had large eyes, suggesting they were visual hunters, and their long, narrow jaws were typically lined with numerous sharp, conical teeth, ideal for catching fast-moving fish and cephalopods like belemnites. Some later, larger ichthyosaurs, such as Dinosaurs from the Triassic, reached lengths of 15 meters or more. A key adaptation for their fully marine lifestyle was their ability to give birth to live young, rather than laying eggs on land, as evidenced by fossils preserving embryos within the mother. This viviparity freed them from returning to shore for reproduction. Plesiosaurs, meaning near lizards, were another major group of marine reptiles that appeared in the late Triassic and diversified extensively throughout the Jurassic and Cretaceous. Plesiosaurs are characterized by their unique body plan: a broad, flat body, 4 large paddle-like flippers, and a relatively short tail. They are typically divided into 2 main groups: long-necked plesiosaurids and short-necked plesiosaurids. Plesiosaurids, such as Elasmosaurus from the Cretaceous, possessed extraordinarily long necks, sometimes comprising more than half of their total body length, which they likely used to ambush fish and cephalopods from below, darting their heads into schools of prey. Their flippers provided propulsion through a powerful synchronized rowing motion. Pliosaurids, on the other hand, were short-necked, massive-headed predators with exceptionally powerful jaws. Kronosaurus, a famous pliosaur from the early Cretaceous, could reach lengths of 10 meters or more, with a skull over 2 meters long. Their robust conical teeth were designed for crushing bones and tearing flesh, indicating they were apex predators, preying on other marine reptiles, large fish, and possibly even sharks. Both plesiosaur groups were air breathers, needing to surface periodically to inhale. Similar to modern whales and dolphins, their powerful flippers and streamlined bodies allowed them to navigate the vastness of Panthalassa and the Tethys Sea with efficiency. Other significant marine reptile groups existed during the Mesozoic. Placodonts, from the Triassic period, were unique for their broad, flattened teeth, which were perfectly adapted for crushing the shells of mollusks and other hard-shelled invertebrates found on the seafloor. Some placodonts, like Placodus, had robust armoured bodies, while others, like Henodus, resembled modern sea turtles. Nothosaurs, also from the Triassic, were more lizard-like in appearance, with long bodies and slender limbs, suggesting they were agile hunters in coastal waters, preying on fish. They likely spent time both in water and on land. In the late Cretaceous, a new group of marine reptiles, the mosasaurs, rose to prominence, becoming the dominant marine predators. Mosasaurs were giant marine lizards, closely related to modern monitor lizards and snakes. They possessed elongated, streamlined bodies, powerful, flattened tails for propulsion, and paddle-like limbs. Their jaws were hinged, allowing them to swallow large prey, and they were armed with sharp, conical teeth. Mosasaurs, such as Mosasaurus itself, could reach lengths of up to 17 meters. They were highly agile and aggressive predators, preying on fish, ammonites, sharks, and even other marine reptiles. Their rapid diversification and global distribution made them a formidable force in the late Mesozoic oceans. The adaptations of these marine reptiles to aquatic life were diverse, but shared common themes. All were air breathers, relying on lungs, and had to surface to breathe. Their limbs evolved into flippers or paddles for efficient swimming. Their bodies became streamlined to reduce drag in water. Many developed specialized teeth for their specific diets, whether fish, mollusks, or other large marine animals. The fossil record of these creatures is rich, often found in marine sedimentary deposits that were once the seafloor of the Tethys Sea or the continental shelves of Panthalassa. These fossils provide compelling evidence of a vibrant and complex marine ecosystem that existed alongside the terrestrial world of dinosaurs, showcasing the remarkable evolutionary capacity of reptiles to conquer both land, air, and sea. While the colossal dinosaurs often capture the imagination, the terrestrial ecosystems of Pangea were teeming with a vast array of smaller creatures that played equally vital, though often less conspicuous, roles in the ancient food webs. These included early mammals, a diverse range of insects, amphibians, and various other small reptiles. Their adaptations, life cycles, and interactions formed the intricate fabric of life that supported the larger, more famous inhabitants of the supercontinent. These smaller organisms were crucial for nutrient cycling, pollination, pest control, and serving as a food source for many predators, including juvenile dinosaurs and smaller theropods. Early mammals, or mammaliforms, emerged during the late Triassic period, evolving from the more advanced cynodont therapsids. These first mammals were typically small, shrew-like, or rodent-like creatures, generally no larger than a modern rat. They were characterized by features such as hair or fur, mammary glands, though direct fossil evidence for lactation is rare, and a more efficient chewing apparatus with differentiated teeth. Unlike their larger synapsid ancestors, which had dominated the Permian, these early mammals occupied nocturnal niches, likely to avoid predation by the larger reptiles and dinosaurs that were active during the day. Their small size and nocturnal habits allowed them to survive and diversify in a world increasingly dominated by dinosaurs. They probably fed on insects, worms, and small plant matter like seeds and spores. Their warm-bloodedness, or endothermy, would have given them an advantage in maintaining a stable body temperature in the fluctuating climate of Pangea, especially during cooler nights or in more temperate regions. The fossil record of these early mammals is sparse, often consisting of isolated teeth or jaw fragments, but these tiny remains provide crucial insights into their evolutionary history and their persistence throughout the Mesozoic era, eventually leading to the diverse mammalian forms of today. Insects were an extraordinarily diverse and abundant group throughout Pangea's existence, playing myriad ecological roles. They had already undergone significant evolutionary radiation by the Permian period, and many modern insect orders were already present during the time of dinosaurs. Dragonflies, cockroaches, beetles, and crickets were common. The high oxygen levels of the late Carboniferous and early Permian may have contributed to the large size of some insects, such as giant dragonflies with wingspans of nearly 1 meter. While oxygen levels decreased by the Triassic, insects remained diverse and numerous. Beetles, in particular, underwent a major diversification during the Mesozoic, occupying niches as decomposers, herbivores, and predators. Cockroaches were ubiquitous scavengers. Crickets and grasshoppers would have been important herbivores, feeding on ferns, cycads, and conifers. The coevolution of insects with plants was a continuous process. While flowering plants were not yet dominant, insects would have played roles in pollinating gymnosperms and dispersing their seeds. Insect larvae, such as those of beetles and flies, would have been vital decomposers, breaking down dead organic matter and recycling nutrients back into the ecosystem. Flying insects provided a crucial food source for early birds, pterosaurs, and small insectivorous dinosaurs. Amphibians, though less dominant on land than reptiles, were still a significant component of Pangea's freshwater and moist terrestrial environments. Large amphibians, known as temnospondyls, which had been prominent in the Carboniferous and early Permian, largely declined after the Permian-Triassic extinction, but smaller forms persisted. Modern amphibian groups such as frogs and salamanders made their first appearance in the Triassic period. These early frogs and salamanders would have inhabited the numerous rivers, lakes, and swamps that dotted Pangea, particularly in more humid coastal regions or along major river systems. Their life cycles, which typically involve an aquatic larval stage, tadpoles, and a terrestrial adult stage, tied them to water bodies. They would have fed on insects and other small invertebrates, and in turn served as prey for small reptiles, fish, and juvenile dinosaurs. Their permeable skin made them vulnerable to desiccation, limiting their distribution to moist habitats and preventing them from colonizing the vast arid interiors of Pangea. Beyond these major groups, a variety of other small reptiles also shared the Pangean landscape with dinosaurs. These included early lizards, snakes, which evolved much later in the Cretaceous, and various other small generalized diapsids. Many of these small reptiles were insectivorous, filling niches as ground-dwelling predators of invertebrates. Some might have been specialized in eating eggs or small vertebrates. Early turtles also appeared in the Triassic, though their exact origins are still debated. These early turtles, such as Progonocales, were terrestrial or semi-aquatic, with a fully formed shell, and would have been slow-moving herbivores or omnivores. Their hard shells provided excellent protection against predators. Small crocodilians and their early relatives were also present, often inhabiting aquatic or semi-aquatic environments, preying on fish, insects, and small vertebrates. The roles of these small creatures in the Pangean ecosystem were multifaceted and indispensable. Insects, in particular, were fundamental to the functioning of the food web. Herbivorous insects consumed plant matter, transferring energy up the food chain to insectivorous amphibians, reptiles, and early mammals. Predatory insects helped control populations of other invertebrates. Decomposer insects and their larvae were vital for breaking down dead plants and animals, recycling nutrients back into the soil, which was essential for plant growth. Early mammals and small reptiles, while often living in the shadow of dinosaurs, occupied crucial niches as consumers of insects and small plant material. and as prey items for smaller carnivorous dinosaurs and other predators. Their presence indicates a complex and interconnected ecosystem, where every size class of animal played a role. The fossil record of these small creatures is often fragmentary, compared to that of large dinosaurs, as their delicate bones are less likely to be preserved. However, discoveries of fossil insects in amber, small mammal teeth, and amphibian skeletons provide valuable insights into their morphology, diet, and distribution. These small animals demonstrate the resilience and adaptability of life, thriving in the shadow of giants and enduring through major environmental changes and extinction events. Their continued evolution throughout the Mesozoic period, often unnoticed by the casual observer, was just as significant as the spectacular diversification of their larger dinosaurian counterparts, laying the groundwork for the ecosystems that would emerge after the end of the dinosaur age. The range of sizes among dinosaurs was truly extraordinary, spanning from creatures no larger than a modern chicken to the most colossal land animals that have ever walked the earth. This vast spectrum of body plans reflects an incredible evolutionary success story, with different dinosaur groups adapting to various ecological niches and environmental pressures across the supercontinent Pangea and its fragmenting landmasses. Understanding the factors that allowed some dinosaurs to achieve such immense sizes is a key aspect of comprehending their biology and ecology. At the smaller end of the spectrum were numerous bird-like theropods and early ornithischians. Many early dinosaurs, such as Eoraptor from the Triassic, were relatively small, around 1 meter in length. Compsognathus, a late Jurassic theropod, was no larger than a turkey, measuring about 1 meter long and weighing only a few kilograms. These small carnivores likely preyed on insects, lizards, and other small vertebrates. Similarly, some early ornithischians, like Lesothosaurus from the early Jurassic, were small, agile bipedal herbivores, reaching lengths of about 1 to 2 meters. These smaller dinosaurs occupied niches similar to modern small to medium-sized mammals and birds, relying on speed and agility to evade larger predators. Their small size allowed them to exploit different food sources and hide in denser vegetation, avoiding direct competition with the larger herbivores and carnivores. The middle range of dinosaur sizes encompassed a wide variety of species. Many theropods, such as Deinonychus from the early Cretaceous, were medium-sized predators, around 3 to 4 meters long, capable of hunting prey larger than themselves, possibly in packs. Ornithopods like Iguanodon from the early Cretaceous were large bipedal or facultatively quadrupedal herbivores, reaching lengths of up to 10 meters. Armored dinosaurs like Stegosaurus, late Jurassic, and Ankylosaurus, late Cretaceous, were also in this range, typically 7 to 10 meters long, relying on their defensive features rather than speed for protection. These mid-sized dinosaurs were abundant and diverse, filling various roles as herbivores, omnivores, or predators of medium-sized prey. The true giants of the dinosaur world were the sauropods, the long-necked, quadrupedal herbivores. These animals achieved sizes that dwarf any other land animal in Earth's history, including the largest mammals. Diplodocus, a well-known late Jurassic sauropod, could reach lengths of over 25 meters, with a significant portion of that length being its neck and tail. Apatosaurus, another Jurassic sauropod, was somewhat shorter but more heavily built. Brachiosaurus, also from the Jurassic, was notable for its exceptionally long front legs, making it one of the tallest dinosaurs, reaching heights of 13 meters or more. In the Cretaceous, sauropods continued to evolve into colossal forms, with some of the largest known dinosaurs, such as Argentinosaurus from South America, estimated to have reached lengths of 35 meters or more and weighing over 70 tons. These immense sizes were a primary defense against predators and allowed them to access vast quantities of high-lying vegetation. Several factors contributed to the ability of sauropods and other large dinosaurs to achieve such colossal sizes. One crucial factor was their unique physiology. Dinosaurs possessed a highly efficient respiratory system, possibly involving air sacs similar to those in modern birds. This allowed for a continuous unidirectional flow of air through the lungs, ensuring highly efficient oxygen uptake. This efficient oxygenation would have supported a high metabolic rate necessary for rapid growth and sustaining a large body. Their skeletal structure, particularly the hollow bones in many sauropods and theropods, provided strength with reduced weight, making it possible to support their massive frames. The abundant food supply of the Mesozoic era was another critical element. The widespread distribution of lush conifer forests, cycads, and ferns across Pangea and its fragmenting continents provided an ample and continuous source of high-calorie plant material. The warm, generally ice-free climate of the Mesozoic meant that growing seasons were long and productive, allowing for the growth of immense plant biomass necessary to sustain such large herbivores. Sauropods, with their long necks, could access vast quantities of foliage without moving their massive bodies extensively, conserving energy. Their digestive systems, likely involving large fermentation chambers and gastroliths, were efficient at breaking down tough plant fibers. The upright limb posture of dinosaurs, with legs positioned directly underneath their bodies, was also a key anatomical advantage. This posture provided efficient support for immense body weight and allowed for more powerful and sustained locomotion compared to the sprawling gait of earlier reptiles. This biomechanical efficiency was fundamental to supporting the evolution of giant forms. Furthermore, the absence of large mammalian competitors until very late in the Mesozoic likely played a role. Mammals, with their higher metabolic rates and different reproductive strategies, did not reach large sizes until after the extinction of the non-avian dinosaurs. This left the large herbivore niches open for dinosaurs to dominate. The evolution of gigantism in dinosaurs was a complex interplay of physiological adaptations, abundant food resources, a favourable climate, and the absence of significant ecological competition from other large terrestrial vertebrates. Understanding how dinosaurs perceived their world requires careful interpretation of fossil evidence, as direct observation is impossible. However, by studying the morphology of their skulls, the structure of their brain cases, the size and orientation of their eye sockets, and comparing these features to modern animals, scientists can make informed speculations about their eyesight, sense of smell, hearing, and other sensory capabilities. These senses were crucial for their survival, enabling them to find food, avoid predators, navigate their environment, and communicate within their species. Eyesight was undoubtedly a primary sense for many dinosaurs, particularly predators and active daytime animals. The size and shape of the eye sockets, orbits, in dinosaur skulls provide clues about the size of their eyeballs. Large orbits generally indicate large eyes, which are often associated with good vision, especially in low-light conditions or for detecting subtle movements. The position of the orbits also offers insights into their field of view and depth perception. Forward-facing eyes, characteristic of many theropods like Tyrannosaurus rex, indicate binocular vision, where the fields of view of both eyes overlap significantly. This provides excellent depth perception, crucial for accurately judging distances when hunting prey. Predators like Tyrannosaurus rex likely had keen eyesight, allowing them to spot prey from a distance and accurately target their attacks. In contrast, many herbivorous dinosaurs, such as sauropods and hadrosaurs, had eyes positioned more laterally on their heads, providing a wider field of view. This panoramic vision would have been advantageous for detecting approaching predators from any direction, though it would have come at the expense of depth perception. The presence of sclerotic rings, bony rings found within the eye sockets of many fossil vertebrates, can provide information about whether an animal was diurnal, active during the day, nocturnal, active at night, or crepuscular, active at dawn and dusk. Large sclerotic rings relative to the orbit size often suggest nocturnal or crepuscular habits, as they indicate a large pupil for gathering light. Smaller rings suggest diurnal activity. While not all dinosaurs preserve sclerotic rings, their presence in some species helps to infer their activity patterns. The sense of smell was also highly developed in many dinosaurs, particularly in theropods. The size and shape of the olfactory bulbs, the part of the brain responsible for processing smells, can be estimated from endocasts, which are molds of the brain cavity within the skull. Theropods like Tyrannosaurus rex had exceptionally large olfactory bulbs, suggesting a highly acute sense of smell. This would have been invaluable for detecting carrion from afar, tracking prey, or locating mates. Even in some herbivores, a good sense of smell could have helped in locating specific plants or detecting predators. The presence of large nasal passages in the skull also supports the idea of a well-developed olfactory system. Hearing in dinosaurs is more challenging to reconstruct, but evidence from the inner ear structures can provide some clues. The cochlea, the part of the inner ear responsible for hearing, can vary in length, with longer cochleae generally indicating a wider range of hearing frequencies. While direct fossilization of soft tissues like the eardrum is rare, the presence and structure of the tympanic notch, a groove in the skull that supports the eardrum, can indicate the presence of an external eardrum. Some dinosaurs, particularly those that may have engaged in vocal communication, likely had good hearing. For instance, the hollow crests of hadrosaurs like Parasaurolophus are thought to have been resonating chambers, used to produce low-frequency sounds for communication over long distances, suggesting they had the auditory capabilities to perceive such sounds. Low-frequency sounds travel well through dense vegetation and over long distances, making them ideal for communication in large, open environments. Other senses, such as touch and taste, are even more difficult to infer from fossil evidence. However, it is reasonable to assume that dinosaurs possessed a sense of touch, particularly through their skin and specialized sensory organs. The presence of whiskers or highly sensitive skin around the snout, as inferred for some tyrannosaurids, could have aided in tactile exploration or sensing vibrations. Taste would have been essential for discerning edible from toxic plants for herbivores, and for evaluating the quality of meat for carnivores. While direct anatomical evidence for taste buds is absent, the presence of a tongue and the overall feeding apparatus imply a functional sense of taste. The overall sensory world of dinosaurs was likely rich and complex, tailored to their specific ecological roles. Apex predators relied on keen eyesight and an acute sense of smell to locate and pursue prey. Large herbivores used panoramic vision and possibly a good sense of smell to detect approaching threats. The evolution of specialized sensory organs, such as the crests of hadrosaurs for sound production, highlights the importance of communication within species. While we cannot fully experience the world as a dinosaur did, the fossil record provides sufficient anatomical clues to reconstruct a plausible picture of their sensory capabilities, revealing them as sophisticated animals navigating a dynamic and challenging environment. The ways in which dinosaurs moved were as diverse as their forms, ranging from the swift, agile strides of small bipedal predators to the ponderous, ground-shaking gaits of colossal, quadrupedal herbivores. Locomotion was fundamental to their survival, dictating their ability to hunt, escape predators, forage for food, and navigate the varied landscapes of Pangea and its fragmenting continents. Scientists reconstruct dinosaur movements through a combination of fossil evidence, including trackways, skeletal anatomy, and biomechanical modeling, providing insights into their speed, posture, and agility. The fundamental division in dinosaur locomotion is between bipedalism and quadrupedalism. Bipedal dinosaurs walked on two legs, primarily their hind limbs. This posture was characteristic of all theropods, the carnivorous dinosaurs, from the earliest Eoraptor to the mighty Tyrannosaurus rex. It also included many ornithopods, such as iguanodon and hadrosaurs, particularly when moving quickly. The evolution of an upright parasagittal limb posture, where the legs were positioned directly underneath the body, was a key innovation for dinosaurs. This stance allowed for more efficient swinging movements of the limbs, reducing the energy cost of locomotion compared to the sprawling gait of earlier reptiles. It also enabled sustained running and greater agility, crucial for active hunting or escaping danger. The tail in bipedal dinosaurs served as a counterbalance, helping to maintain stability during movement, especially when changing direction rapidly, and also aided in turning. The presence of strong muscle attachment sites on their leg bones indicates powerful musculature for propulsion. Quadrupedal dinosaurs walked on all four legs. This was the primary mode of locomotion for the colossal sauropods, such as Diplodocus and Brachiosaurus, as well as heavily armoured dinosaurs like Ankylosaurus and the horned dinosaurs like Triceratops. For sauropods, their pillar-like legs were adapted to support immense body weight, distributing pressure evenly across all four limbs. Their movement was ponderous, but powerful. Trackways of sauropods show wide footprints, indicating a broad stance, and suggest a relatively slow, deliberate pace, likely similar to modern elephants. While they were not built for speed, their sheer bulk provided formidable defense. The feet of sauropods were often fleshy, acting like cushions to absorb the immense impact of each step. For armoured dinosaurs, quadrupedalism provided a stable platform for their heavy bony plates and spikes. Their gaits would have been slow, but their defensive features made speed less necessary for survival. Triceratops and other ceratopsians, with their robust limbs, were capable of powerful charges, using their horns defensively. Some dinosaurs exhibited facultative bipedalism or quadrupedalism, meaning they could switch between walking on 2 or 4 legs depending on the situation. Many hadrosaurs, for instance, were primarily bipedal but could drop to all fours to graze on low-lying vegetation or possibly to gain stability. Early prosauropods, ancestors to the giant sauropods, also showed this versatility, transitioning from a more bipedal stance in their earlier forms to a more quadrupedal one as they grew larger. This flexibility in locomotion allowed them to exploit a wider range of food sources and navigate diverse terrains. Estimating the speed of dinosaurs is challenging and relies heavily on fossilized trackways and biomechanical models. Trackways provide direct evidence of stride length and foot placement, which can be used to calculate approximate speed. For example, some theropod trackways indicate speeds of up to 25 to 40 km per hour for animals like Carnotaurus, suggesting they were capable of fast sprints. However, top speeds for larger dinosaurs like Tyrannosaurus rex are highly debated. While early estimates suggested speeds up to 70 km per hour, more recent biomechanical studies, considering the stress on bones and muscles, suggest a more modest top speed of around 20 to 30 km per hour, possibly closer to the speed of a fast human runner, with an emphasis on powerful acceleration over sustained high speed. Large sauropods, as indicated by their trackways and skeletal structure, were likely limited to walking speeds, perhaps 5 to 10 km per hour. Their movement was about efficient energy use over long distances rather than bursts of speed. Beyond the terrestrial dinosaurs, 2 other major groups of reptiles shared the Mesozoic world and had their own unique modes of movement: the flying pterosaurs and the marine reptiles. Pterosaurs, the first vertebrates to achieve powered flight, soared through the skies above Pangea. Their wings were formed by a membrane of skin stretched from an enormously elongated 4th finger to their ankles. They achieved propulsion through flapping their wings, similar to birds, and were capable of sustained powered flight, as well as efficient soaring. Their skeletons were lightly built with hollow bones and air sacs to reduce weight. On the ground, pterosaurs were quadrupedal, walking with a somewhat awkward gait on their folded wings and hind legs. Larger forms, like Quetzalcoatlus, might have used a powerful spring-like launch from all fours to become airborne. Marine reptiles, which were not dinosaurs but had returned to the ocean from terrestrial ancestors, evolved highly specialized adaptations for aquatic life. Ichthyosaurs, with their streamlined, fish-like bodies, moved through water by powerful side-to-side undulations of their large, crescent-shaped tail flukes, much like modern fish and dolphins. Their flippers were primarily used for steering and stability. Plesiosaurs, with their broad bodies and 4 large paddle-like flippers, propelled themselves through the water with a unique underwater flight or rowing motion, using their flippers in a coordinated fashion to generate thrust. Their long necks, in plesiosaurids, provided agility for catching fish, while their short, powerful tails helped with steering. Mosasaurs, the dominant marine predators of the late Cretaceous, propelled themselves primarily with powerful side-to-side movements of their elongated, flattened tails, reminiscent of eels, while their paddle-like limbs were used for steering and stability. Each group of these ocean dwellers, from the fastest ichthyosaurs to the agile mosasaurs and the unique plesiosaurs, represented a distinct evolutionary solution to the challenges of navigating a vast aquatic environment. The social lives of dinosaurs, particularly the question of whether they lived in herds or other organized groups, is a fascinating area of study primarily inferred from fossil evidence rather than direct observation. While conclusive proof of complex social structures like those of modern mammals is elusive, a significant body of evidence suggests that many dinosaur species engaged in some form of group living, exhibiting herd behavior, communal nesting, and possibly even migratory patterns across the vast landscapes of Pangea and its fragmenting continents. The most compelling evidence for dinosaur herd behavior comes from bone beds, which are fossil sites containing the remains of numerous individuals of the same species found together. These mass graves are often interpreted as evidence of a catastrophic event, such as a flood or drought, that killed an entire herd simultaneously. For example, large bone beds of the Jurassic sauropod Apatosaurus and the ornithopod Camptosaurus have been found, suggesting these large herbivores moved in groups. Similarly, extensive bone beds of Cretaceous hadrosaurs, like Maiasaura and Edmontosaurus, are strong indicators of herd living. The sheer number of individuals found together, across different age groups, is difficult to explain without the assumption of group cohesion. Another critical line of evidence comes from fossilized trackways. Multiple parallel tracks of the same dinosaur species, moving in the same direction, strongly suggest that these animals were traveling together in a group or herd. Such trackways have been found for various dinosaur groups, including sauropods and ornithopods, in locations across North America, Europe, and Africa. These parallel tracks, sometimes extending for hundreds of meters, provide direct behavioral evidence of coordinated movement, indicating that these dinosaurs were not solitary wanderers. The spacing of the tracks can sometimes even offer clues about the density and structure of the herd. Communal nesting sites provide further insights into dinosaur social lives, particularly concerning reproduction and parental care. The famous Egg Mountain site in Montana, discovered in the 1980s, revealed multiple nests of the Hadrosaur Maiasaura, meaning good mother lizard, clustered together over many generations. Each nest contained dozens of eggs, and evidence suggests that young Maiasaura remained in the nests after hatching, implying parental care or at least communal rearing. The close proximity of these nests, spaced just about a dinosaur's length apart, suggests colonial nesting, a behaviour seen in many modern birds, which are avian dinosaurs, and reptiles, offering protection against predators through sheer numbers. Similar communal nesting grounds have been found for other dinosaur species, indicating that nesting in groups was a widespread reproductive strategy. The benefits of group living for dinosaurs would have been substantial, especially for large herbivores. Herd behaviour provides enhanced defence against predators. In a large group, there are more eyes and ears to detect threats, and predators are less likely to single out an individual. Large herds could also engage in collective defence, intimidating or even repelling attackers through sheer numbers or coordinated actions, such as presenting an impenetrable wall of armoured bodies or powerful tails. For example, ceratopsians like Triceratops, with their horns and frills, might have formed defensive circles, protecting their young or vulnerable members within the group, similar to musk oxen. Group living also offers advantages in foraging and resource acquisition. In a vast, uniform environment like parts of Pangea, herds could more efficiently locate food sources and migrate to areas with abundant vegetation. Cooperative foraging, where multiple individuals search for food, could increase the overall success rate for the group. For plant eaters, moving in large herds might have allowed them to exploit vast areas of vegetation more quickly before moving on, preventing overgrazing in a single location. Migration across Pangea was also likely a common behaviour for many large herbivorous dinosaurs, driven by seasonal changes in vegetation and water availability in the supercontinent's interior. The continuous landmass of Pangea, stretching from pole to pole, would have presented unique challenges and opportunities for long-distance movements. While direct evidence for specific migratory routes is scarce, the widespread distribution of certain dinosaur species across continents that were once connected, e.g. some sauropods found in both North America and Africa before the Atlantic fully opened, suggest that they were capable of traversing vast distances. These migrations would have been critical for survival in the face of Pangea's often extreme climate, moving between wetter and drier regions or warmer and cooler areas as seasons changed. Communication within these herds would have been essential for maintaining cohesion and coordinating movements. While vocalizations are difficult to infer directly from fossils, the hollow crests of some hadrosaurs, like Parasaurolophus, are believed to have functioned as resonating chambers, producing low-frequency sounds that could travel long distances and communicate over varied terrain. Visual displays, such as the elaborate frills of ceratopsians or the crests of hadrosaurs, may have also played a role in species recognition, signaling social status or courtship displays within the herd. The social lives of dinosaurs, though often inferred from indirect evidence, paint a picture of complex behaviours that enabled them to thrive and dominate terrestrial ecosystems for millions of years. The reproduction of dinosaurs, like all non-avian reptiles, involved the laying of eggs. The study of fossilized dinosaur nests, eggs, and embryonic remains provides invaluable insights into their egg-laying habits, nesting strategies, clutch sizes, and even hints about parental care. These discoveries have transformed our understanding of dinosaur biology, moving beyond the image of solitary, simple creatures to reveal complex reproductive behaviors. Dinosaur nests varied considerably depending on the species and environment. The simplest nests were shallow depressions or scrapes made in the ground, where eggs were laid directly. Other dinosaurs built more elaborate mounds of sand or soil, sometimes mixed with vegetation, which might have served to incubate the eggs through the warmth generated by decaying plant matter, similar to some modern reptiles or birds. The choice of nesting site was crucial for the survival of the eggs and hatchlings. Many dinosaurs, particularly herbivores, opted for open, flat areas near water sources, such as floodplains, riverbanks, or lake shores. These locations provided accessible food and water for the young upon hatching. The substrate for nests often consisted of sandy or silty sediments, which were easy to excavate and provided good drainage. One of the most significant discoveries related to dinosaur nesting came from the Egg Mountain site in Montana in the 1980s. This site revealed extensive colonial nesting grounds of the Hadrosaur maiasaura, meaning good mother lizard. Multiple nests found closely packed together over several layers indicated that maiasaura returned to the same nesting sites year after year, suggesting a communal nesting behavior. Each nest was a bowl-shaped depression, approximately 2 meters in diameter, large enough to contain about 25 to 40 large spherical eggs. The consistent spacing between nests, roughly one adult maiasaura body length apart, suggests that mothers remained near their nests, implying a degree of territoriality even within a communal setup. Fossilized dinosaur eggs themselves provide a wealth of information. They vary in shape, from spherical to elongated or ovoid, and in size, from as small as a chicken egg to up to 30 centimeters in length. The shell texture can range from smooth to highly ornamented with pores, ridges, or nodes. The presence of pores on the eggshell is vital for gas exchange, allowing the developing embryo to breathe. Microscopic analysis of eggshell structure can sometimes distinguish between different dinosaur groups. Fossilized embryos found within eggs offer direct evidence of the developmental stages and morphology of hatchlings, revealing that many dinosaur babies resembled miniature versions of their parents. Clutch size, or the number of eggs laid per nest, also varied among species. Some theropods, like Oviraptor, are known to have laid clutches of 15 to 20 eggs in a spiral pattern within a mound-like nest. These spiral arrangements suggest careful placement by the parent. Larger sauropods also laid multiple eggs, though often in less structured clusters. The number of eggs laid per clutch reflects a balance between reproductive investment and parental care. Species that laid more eggs might have provided less individual care to each hatchling, while those with fewer eggs might have invested more in their offspring's survival. The question of parental care in dinosaurs is a subject of ongoing research, but fossil evidence provides compelling hints of its existence in some groups. The maiasaura nesting sites at Egg Mountain, for instance, showed that the juvenile dinosaurs remained in the nest for some time after hatching, reaching a size of over 1 meter. Their bone structure at this stage was not robust enough for extensive foraging on their own, suggesting that the parents brought food to them or guarded them within the nest until they were large enough to venture out. This indicates post-hatching parental care, a behavior more common in birds than in most modern reptiles. Evidence from other nesting sites, like those of Oviraptor, where an adult skeleton was found crouched over a clutch of eggs in a brooding posture, further supports the idea of parental incubation and protection. The choice of egg-laying environment was also critical. While many nested in open areas, some dinosaurs may have used more secluded spots. The development of hard-shelled amniotic eggs was a crucial evolutionary innovation that allowed dinosaurs, like other reptiles, to reproduce entirely on land, freeing them from a dependence on aquatic environments for larval stages, unlike amphibians. This adaptation was fundamental to their colonization and diversification across the terrestrial landscapes of Pangea. The high reproductive output, often involving multiple eggs per clutch, combined with varying degrees of parental care, contributed to the success of dinosaurs in colonizing diverse environments and maintaining large populations over millions of years. These fossil nests and eggs are direct windows into the reproductive strategies and early life histories of these ancient giants. The journey of a dinosaur from a tiny embryo within an egg to a colossal adult was a remarkably rapid and perilous one, often marked by astonishing growth rates and, in some species, a degree of parental care. While direct observation of dinosaur life is impossible, fossil evidence from nests, eggs, embryos, and juvenile skeletons provides invaluable insights into the early lives of these magnificent creatures, revealing complex reproductive strategies and life histories. All known non-avian dinosaurs laid eggs, similar to modern reptiles and birds. The hatching process would have been a vulnerable moment for the young. Evidence suggests that some dinosaur hatchlings, much like modern birds and crocodiles, possessed a temporary egg tooth, or a hardened bump on their snout, used to break through the tough outer shell of their egg. Once free from the confines of the egg, the newly hatched dinosaurs, often referred to as neonates, were remarkably small relative to their potential adult size. For instance, a hatchling sauropod, destined to become a multi-ton giant, might have been no larger than a small bird or a rabbit. This immense disparity in size meant that baby dinosaurs faced unique challenges and vulnerabilities. The growth rates of dinosaurs were exceptionally fast, especially in larger species. Studies of bone histology, which involves analysing microscopic growth rings preserved within fossilised bones, indicate that dinosaurs grew at rates comparable to, or even faster than modern birds and mammals, far exceeding the growth rates of modern reptiles. This rapid growth allowed them to quickly escape the most vulnerable stages of their lives, reducing the time they were susceptible to predation by larger carnivores. For example, large sauropods are estimated to have reached near adult size in as little as 10 to 15 years, a staggering pace for such massive animals. This rapid growth required an immense intake of nutrients, particularly for herbivores, necessitating constant feeding. The transition from hatchling to adult involved significant changes in body proportions, a process known as ontogeny. While some dinosaurs exhibited isometric growth, meaning their body parts grew proportionally throughout their lives, many showed allometric growth, where certain body parts grew at different rates. For instance, the heads of many juvenile theropods might have been relatively larger compared to their adult counterparts, and their limbs proportionally longer for greater agility. As they matured, their bodies would fill out, and their defensive or specialized structures such as horns, frills, or massive claws would fully develop. This change in proportions often meant that juveniles occupied different ecological niches than adults, potentially reducing competition within their own species. Juvenile carnivores might have hunted smaller prey than their parents, while young herbivores might have browsed on different types of plants or at lower levels. The life of a baby dinosaur was fraught with peril. Their small size made them easy prey for a wide range of predators, including other reptiles, mammals, birds, and even smaller carnivorous dinosaurs. They would have also faced environmental hazards such as floods, droughts, and disease. The very act of leaving the nest and venturing into the wider world for the first time would have been a perilous journey. The rapid growth strategy was a key evolutionary response to these pressures, allowing them to quickly reach a size where fewer predators posed a threat. Evidence for parental care in dinosaurs, particularly post-hatching care, comes from a few remarkable fossil discoveries. The most famous example is the Hadrosaur maiasaura, meaning good mother lizard, from the Egg Mountain site in Montana. Here, nests containing multiple eggs and juvenile skeletons of varying sizes were found in close proximity. The juveniles, measuring up to 1 meter in length, were too large to have been recent hatchlings, yet their bones were not robust enough for extensive foraging on their own. This strongly suggests that maiasaura parents, or other adults in a communal group, returned to the nest to feed and protect their young until they were capable of fending for themselves. The wear on their teeth indicates they were consuming plant material, likely brought to them by adults. Other evidence for parental care comes from discoveries of an adult oviraptor skeleton, found brooding over a clutch of eggs, protecting them similar to how a bird incubates its nest. While this primarily indicates incubation and nest guarding, it suggests a level of parental investment beyond just laying eggs. Some paleontologists also propose that the presence of multiple tracks of varying sizes moving together may indicate family groups travelling with their young, especially for species like sauropods and ornithopods that formed herds. However, the extent and duration of parental care likely varied significantly among different dinosaur groups, with some species providing extended care and others leaving their hatchlings to fend for themselves shortly after emergence, similar to modern reptiles like sea turtles. The communal nesting sites of Maiasaura suggest that young dinosaurs often grew up in a group setting, benefiting from safety in numbers and perhaps collective protection. This social environment would have been crucial for learning and survival during their vulnerable juvenile stages. The transition from dependent juvenile to independent adult involved not only physical growth, but also the development of hunting skills for carnivores, foraging strategies for herbivores, and social behaviours necessary for integration into adult groups. The perilous yet rapid journey from egg to adult highlights the intense selective pressures that shaped dinosaur life histories and contributed to their extraordinary evolutionary success. The constant threat of predation from formidable carnivorous dinosaurs drove the evolution of an astonishing array of defensive strategies among their herbivorous counterparts. These defences range from passive attributes like immense size and protective armour to active weaponry such as sharp spikes, formidable horns, and powerful tail clubs, as well as behavioural adaptations like camouflage and herd living. This ongoing evolutionary arms race between predator and prey shaped the diverse forms and features of dinosaurs throughout the Mesozoic era. One of the simplest yet most effective defences for many large dinosaurs was sheer size. The colossal sauropods, such as Argentinosaurus and Brachiosaurus, grew to such immense proportions that a full-grown adult would have been virtually invulnerable to even the largest theropod predators. While juveniles and subadults might have been susceptible, a mature sauropod presented a challenge too great for any single predator to overcome. Their massive bulk alone acted as a deterrent, as the energy expenditure and risk involved in tackling such an animal would have been enormous. Their long, powerful tails could also have been used as whips, capable of delivering devastating blows to any attacker that came too close. Another widespread form of defense was passive armor. Ankylosaurs, meaning fused lizards, were the ultimate armored dinosaurs, particularly prevalent in the Cretaceous period. Dinosaurs like Ankylosaurus were heavily built, quadrupedal herbivores covered from head to tail in thick bony plates, or osteoderms, embedded within their skin. These osteoderms formed a formidable, often interlocking shield of bone that made them virtually impervious to attacks from above. Their eyelids were even covered with bone. This passive armour provided excellent protection against the slashing claws and biting jaws of large theropods. Their low-slung, broad bodies also made them difficult to flip over, further enhancing their defensive capabilities. Stegosaurs, such as Stegosaurus from the late Jurassic, featured another unique form of passive defense, the distinctive double row of large, upright, bony plates along their backs. While the exact function of these plates is debated, they may have provided some degree of protection to the vulnerable spinal column, or served as a visual deterrent. More definitively, stegosaurs possessed a formidable weapon at the end of their tails, a cluster of 4 sharp, bony spikes known as a thagomizer. This spiked tail was capable of swinging with considerable force, as evidenced by puncture wounds found on the fossilized bones of predators like Allosaurus, indicating its effective use in active defense. Horns and frills were the hallmark defenses of ceratopsian dinosaurs, which thrived in the late Cretaceous. Triceratops, perhaps the most famous, sported 3 sharp horns, 2 long ones above its eyes and a shorter one on its snout, along with a massive solid bony frill protecting its neck and shoulders. These features were undoubtedly used in active defense against large predators like Tyrannosaurus rex. A charging Triceratops, weighing several tons and armed with powerful horns, would have been a terrifying prospect for any attacker. The frill, while protecting the neck, also served as a large surface for display, possibly deterring rivals or attracting mates. Other ceratopsians exhibited a wide variety of horn and frill configurations, suggesting different defensive strategies and recognition signals. Beyond specialized weaponry, many dinosaurs relied on more general defensive attributes. Speed and agility were crucial for smaller bipedal dinosaurs to escape predators. Many ornithopods and smaller theropods possessed long, powerful legs adapted for rapid acceleration and sustained running, allowing them to outrun potential threats. Hadrosaurs, for instance, despite their size, were capable of bipedal bursts of speed. Camouflage, though impossible to confirm directly from the fossil record, was likely employed by hundreds of millions of years ago, long before the world took the shape we know today. All land on Earth was joined together in one vast supercontinent. This enormous landmass, known as Pangea, stretched from pole to pole and held within it deserts larger than modern countries, endless forests and coastlines that faced a single massive ocean. Life flourished in ways both strange and spectacular. Reptiles grew to giant sizes, early dinosaurs emerged, and bizarre plants covered the land. It was a world of extremes, shaped by shifting climates and the slow, unstoppable movement of the Earth itself. Exploring Pangea reveals a story of survival and transformation, where landscapes twisted and cracked, and creatures adapted to a planet in constant motion. It was here that some of the most extraordinary chapters of Earth's history began, setting the stage for the rise of the dinosaurs. Before we dive into this ancient supercontinent, share in the comments where you're watching from and what time it is for you. Then get ready to journey back to the age of Pangea, a time when all the world was one. The story of Earth's continents before the emergence of Pangea is a tale of immense geological time, spanning billions of years and involving the slow, relentless dance of tectonic plates. Our planet began as a molten ball, a chaotic swirl of rock and metal, roughly 4.5 billion years ago. In its earliest phase, known as the Hadean Eon, the surface was too hot for solid land or liquid water to persist. Intense volcanic activity was constant, and the planet was frequently bombarded by asteroids and comets, remnants from the formation of the solar system. As the Earth gradually cooled, a thin, unstable crust began to form, only to be repeatedly melted and reformed by the planet's internal heat and external impacts. Over hundreds of millions of years, water vapor released from volcanic eruptions condensed to form the first oceans, and the continuous cooling allowed more stable, though still dynamic, land masses to emerge from the global ocean. These earliest continental fragments were small, likely no larger than modern-day islands or microcontinents, and were composed of primitive granitic rocks. During the Archean Eon, which followed the Hadean and lasted from approximately 4 billion to 2.5 billion years ago, the Earth's crust continued to thicken and stabilise. The process of plate tectonics, though perhaps operating differently than today, began to slowly assemble these small land masses into larger, more cohesive blocks. The exact configuration and timing of these early continental assemblies are difficult to reconstruct due to the immense age and subsequent geological reworking of the rocks. However, geological evidence suggests the formation of the very first protocontinents. These were not continents in the modern sense, but rather collections of smaller crustal pieces. One of the earliest proposed supercontinents, Volcanic, is thought to have formed around 3.6 billion to 3.1 billion years ago, comprising parts of what are now South Africa and Western Australia. Its existence is inferred from similarities in ancient rock formations and magnetic signatures. Following Volcanic, another early supercontinent, is hypothesized to have formed about 3 billion years ago. Was not a global supercontinent, but was likely the largest landmass on Earth at the time, containing parts of modern-day Africa, India and Australia. These early continental nuclei were relatively stable and grew over time through the accretion of volcanic island arcs and smaller crustal fragments. The Proterozoic Eon, from 2.5 billion to 541 million years ago, witnessed significant advancements in both continental assembly and the evolution of life. This eon is characterized by the formation and breakup of several major supercontinents, a cycle that would eventually lead to Pangea. Around 2.7 billion to 2.5 billion years ago, the supercontinent Kenneland is believed to have formed, encompassing large parts of what are now North America, Greenland, Scandinavia, and parts of Siberia. Kenneland's breakup, driven by mantle plumes and rifting, occurred around 2.4 billion to 2.1 billion years ago, leading to widespread glaciation events, possibly due to changes in atmospheric carbon dioxide levels. Following Kenneland, the supercontinent Columbia, also known as Nuna, assembled between 2.1 billion and 1.8 billion years ago. Columbia was a vast landmass that included nearly all of Earth's continental blocks at the time, stretching from what is now North America to Siberia, Australia and Antarctica. Its formation involved a series of continent-continent collisions, creating extensive mountain belts, Columbia remained stable for several 100 million years before beginning to fragment around 1.3 billion years ago. The most well-understood supercontinent preceding Pangea was Rodinia, which assembled around 1.1 billion years ago. Rodinia was a massive landmass centered near the equator, and its formation involved the collision of several continental blocks, including Laurentia, Proto-North America, Baltica, Proto-Europe, Siberia, Amazonia, and the vast landmass of Gondwana. The assembly of Rodinia resulted in the closure of ancient oceans and the formation of extensive mountain ranges. The climate during Rodinia's existence was complex, with evidence suggesting periods of extreme cold, including the snowball Earth events, where the planet may have been almost entirely covered in ice. The breakup of Rodinia began around 750 million years ago, a process that was slow and protracted, continuing for hundreds of millions of years. This breakup created new ocean basins, such as the Iapetus Ocean and the Panthallassic Ocean, and led to the dispersal of continental fragments. These fragments would eventually reassemble in new configurations. Alongside these grand geological transformations, life on Earth was also undergoing profound changes. The very first life forms were single-celled organisms, prokaryotes, that emerged in the Archean Eon, perhaps as early as 3.8 billion years ago, thriving in the primordial oceans. These early life forms were anaerobic, meaning they did not require oxygen, as the early Earth's atmosphere had very little free oxygen. Around 3.5 billion years ago, photosynthetic organisms, particularly cyanobacteria, began to evolve. These microscopic life forms use sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. This seemingly simple biological innovation had a revolutionary impact on the planet. Over hundreds of millions of years, the cumulative effect of oxygen production by cyanobacteria led to the Great Oxidation Event around 2.4 billion to 2.1 billion years ago. This event saw a dramatic increase in atmospheric oxygen levels, which was toxic to many existing anaerobic life forms, but paved the way for the evolution of more complex oxygen-breathing organisms. Evidence of these early photosynthetic communities